Okay, we can just connect, because you have a USB-C, right?
Yeah,
so
yeah.
you can just connect this to your laptop. Okay, let's just do it like this. Okay. So, I see. Are we set up with the stream and everything? Okay, very good. Well, okay then. So, hello everyone. I'm Aleksander Boruch-Guszecki. I'm one of the organizers, and I just wanted to say a few words before we begin. So I didn't organize this myself. There's been 3 other people participating. Unfortunately, I don't see any of them in this room. It seems that 2 of them unfortunately had trouble coming to Splash, and one of them might be just late. So I wanted to begin with a short story. I promise it's not going to be too long. I met James Noble, another organizer, last year at Splash in Auckland, New Zealand. So he was talking to Maya Milano, another of the organizers at the time, and I wanted to spend my time productively at the conference, meet some of the legends. So I walked up to James Noble and I said hi, right? I said that I'm working with Martin Oderski on this idea to track capabilities in the type system of Scala. I chatted to James Noble for like 5 minutes, and clearly he must have decided that I was a very reasonable fellow, because he told me and Maya, how about we organize IWACO, right? So that's all it took. That's how he got me, right? Sometimes that's really just how much it takes. Yeah, so that was the beginning. Those were the 3 organizers, and then Tobias Rikstad joined at some point a bit later on. And honestly, it's been great fun to organize this edition of IWACO. It's been a bit of work, sure, but it's mostly been great fun. And it's been, I'm really happy to see so many people come here to listen about the topics of the workshops, of this workshop. And I find them quite interesting, Otherwise, I wouldn't be working on them. So it's aliasing capabilities and ownership. I heard this I heard the name of the workshop like 3 years ago, and back then it seemed to me like just random topics that seemed to be gathered together. But actually, yesterday when I started thinking what I want to say, I noticed that all of these things, they seem quite connected. They seem intricately connected, right? So let's see. So let's make sure that we are on the same page. So what are capabilities? The capability is, you can think of it as an object that guards access to some functionality, right? Like an example is a file handle. You need a file handle to access the disk, right? The operating system creates it, gives it to a program. It's a capability to access the file, file system. So that's the basic idea, right? And then we have aliasing. So aliasing means tracking aliases of something, right? Knowing what are other names for some entity. But like, what entities do you want to keep track of their aliases, right? You don't want to keep track of the aliases of the integer 1. Like, clearly the entity, it needs to give you access to some functionality, right? So you want aliasing, so you invite capabilities into your system, right? Or like, you connect the two. And ownership is the same, right? Ownership is basically a way of saying that I control the aliasing of some entity, right? Maybe I can give it out to someone, but then I take it back, right? Or maybe I can like, just decide to drop it permanently. But I own the aliases of this thing, essentially, right? And it's the same thing, right? This entity needs to be important, right? So you have one of those, and you invite the other. It's like this very interesting intertwined triangle. And it's not only interesting, like these are quite enduring concepts with a long history of research and application. I think it spans like 5 decades or more, and it's still counting, right? So it's enduring in the sense when they are like enormous areas that it's quite impossible for me to do them justice in like 15 minutes. James Noble has a session where has a talk where he covers part of the history, and it takes him like 2 hours, and he needs to zoom through everything. He basically just tells you titles of the papers. So, so there is a lot of research and work done on the topic. And it's enduring in the sense that they are very, very relevant topics. Hello, James. I mean, the world just seems to, really want to have capabilities and to control their aliasing and ownership, right? I mean, the reasons which are the most salient to me right now would be safe memory management, fearless concurrency, and security in a cloud computing setting. It's basically these things, right? There is a number of high-profile ongoing projects in the area, in academia and in the industry, and there is a steady stream of research papers. So, like, I mean, this is one of the things that is still crazy to me. Rust was voted the most beloved programming language in the Stack Overflow survey, like 7 times in a row, 7 years in a row, right? So developers are basically screaming that they want more of this stuff, right? So clearly, very, very relevant topics, and the techniques, they are incredibly broad, applied to these topics. So they range from hardware solutions, there's hardware, there is language design, and there is type systems and formal verification. The span is very, very broad, right? So hopefully, I definitely hope so, this workshop should provide you with lots of opportunities to make new and interesting contacts. And if you are younger and interested in these topics, if you are a junior researcher, then I definitely hope that it will help you broaden your horizons and look for research opportunities. And I'm very happy. I mean, it's been a privilege to try and build something that will provide something like that. So I'm quite excited to hear what everyone has to say. And I hope you are as excited as I am. Welcome to Iwako.
So I'm the other co-organizer, or perhaps I should say co-disorganizer, given that neither Meg nor Tobias have managed to be here. Through the wonders of Ursula timetabling, I believe I am double booked. Including with an invited talk just over there, so I will unfortunately be in and out more than I would like to be, because I do try and get to Iwako. Thanks for coming. We're not scary. I missed the start because I was having a headache. Did you talk about the plan? And yeah, so there's a discussion session in the afternoon.
I see.
Did you? Did you know? Did you talk about what's going to happen? We're going to start with Martin, who I have introduced several times. I think I introduced, was there a Dalnagan introduction? I think I remember. Yeah, that's right. So it's always my pleasure to introduce Martin, which I will now do so his student doesn't have to. Is that EFPL? That's just gorgeous.
That is, yeah, that's the learning center at EPFL. Yeah.
That's that, yeah, yeah. I don't think I've ever visited. I'm sure I should. I didn't realize it was that gorgeous. And is it fair to say that I think the Swiss have a great heritage in programming language design and in architecture and in design generally? So we have to guess what Martin's font is.
I actually don't know.
It's probably Helvetica, isn't it?
It might be Calibri. It's not Helvetica. I don't think it's Helvetica.
It's not Helvetica.
I don't think it's Helvetica.
Yeah, if I had my Swiss watch on, I would have been here on time. But it's certainly a very modern, very clean font. And that built, you know, and then if you think about, of course, a famous Swiss programming language, Pascal, designed by Niklas Wirth, which, you know, people have said it's designed like a Swiss watch. Every little bit fits inside every other little bit, which fits inside every other little bit, because your program should be a syntactic and a semantic tree defined recursively, and that's really what Pascal is, and that's this whole idea of clean lines, simple definitions, modernism, which you can see in that building, and which the kind of complexity you often face if you allow aliases and if you allow mutable state into your programming language. Oh, cool, I can keep ranting so Martin can switch off his phone, and then you won't realize I've gone. That idea of modernism, that idea of clean lines, of clean definitions. And the thing about that building is it looks simple, but that building couldn't have been designed or made to stand up 20 or 30 years ago, because the subtle shapes and the subtle curves you can see in that building can only be done and verified using CAD techniques, using computers and using computer systems that look simple, but it's really, really complicated if you want to make something that looks simple. And I'm always happy to push that when I'm talking to Martin. I do think he is definitely the most talented compiler writer of our generation. I've known him for, I remember seeing you in South Australia, where you'd moved in order to enjoy the warm weather.
That's slightly less.
And yeah, your fate did not leave you in the Southern Hemisphere. I'm delighted to introduce Martin, who's talking about what I really think is one of the really clever, or the clever ideas that have emerged in the last few years in this area, capture tracking.
Thank you. Thank you, and this was a great extempore thing about this building you knew nothing about, but yeah, so but I can stay on, yeah, I mean, it's all correct. So the building was actually designed by a pair of Japanese architects who got the Pritzker Prize later on. And if you look at it from the air, it looks like a Swiss cheese. There are lots of holes in it. It looks like a Swiss cheese that you put on the heating so that it gets slightly wobbly. And the secret behind that is not just computer design, but absolutely tons of concrete. So I remember we did a little extension where we needed 15 square meters of concrete that high, and we couldn't get them for a whole week because that building was constructed and essentially all the concrete in the canton was earmarked towards that building, because that's essentially a meter thick. So Swiss architects were actually very critical about that at first, because it's not at all resource conscious. So the CO2 footprint of this thing was gigantic. Okay, anyway, let's not talk about the building. Let's talk about this thing here at the bottom, Scala, and how we do capture tracking in Scala. And I should also say that this is joint work with some people in this room, Alex, Ed, some people not here, Jonathan, Andre Lotak, Yichen should be here. No, other people will show up, I guess. Okay, Jonathan is here, yeah. Speak of the devil, yeah. just talked about you in the collaborators. Okay, so I'm going to do this from the back forward. So I'm going to talk about Scala a little bit and why I believe that capture tracking, or generally aliasing ownership, is an important thing for Scala to acquire. You could say, well, Scala is already a fairly rich language, so why would we want to add this? So I think one of the reasons is that Scala, with a with some other languages, which we also know and like well, was quite unique 12 years ago. It was unique in the space to have, to be fairly strong on functional programming and at the same time have fairly good, strong static type systems. And of course, you can go further. So then there's always Haskell if you want both functional programming and excessive types. But these languages sort of struck a nice balance. And whereas the industry was essentially here at the bottom and at the left, so they had nothing of functional programming, and a lot of them were dynamically typed. That was, in 2010, still a big thing where people were arguing that dynamic is better than static. So if we look at what happened since then we see that all these other languages made a trajectory into the sweet spot here. So Java got lambdas, and now it even got records and pattern matching. Python got PyPy, optional types. All these languages got JavaScript, got TypeScript, Ruby got sorbet, Lisp got contracts and typed racket, and all these things. Essentially, they all got type systems, and the more imperative languages acquired functional features at a furious pace, you could say. So that right now, where we are is essentially here. They're all moved very close to essentially where Scala, OCaml, F# were. And there's also a lot of newcomers, Kotlin, Swift, Rust, that also are somewhere in this space. Some of them are more functional, some of them are less, but all of them are pretty okay on that side, and all of them have fairly expressive type systems. So Scala has lost its role of uniqueness. You could say, well, imitation is the greatest form of flattery, and indeed you find many, many features that were pioneered in Scala. I'm not saying invented in Scala, but essentially first pioneered for a mass audience that other languages picked up. So Scala is no longer alone in its space, and I believe it is by now a lot cleaner, smaller. In fact, if you look at the grammars, all these languages are much, much bigger than what Scala is, and more expressive than most of the other languages. But to what degree does that matter? So that's one thing. The other thing is a cultural thing, and that was actually previewed even in 2009. So James Irie, who wrote this blog post, A Brief, Incomplete, and Mostly Wrong History of Programming Languages. It's hilarious. If you don't know it, you should definitely read it. It's about, essentially, he has something to say about most programming languages out there, usually quite mean. It ends with this one here. A drunken Martin Udelsky sees a Reese peanut butter cup ad featuring somebody's peanut butter getting on somebody else's chocolate and has an idea. He creates Scala, a language that unifies constructs from both object-oriented and functional languages. This pisses off both groups, and each promptly declares jihad. And that was actually very prescient. In 2009, I laughed about it and said, well, good joke. But what actually happened since then in the Scala community is a lot of fighting between pure functional people and essentially people who like their effects and their objects and things like that. So the question then is where Scala is, what should it become? Where do we want to evolve it to? So some people think that Scala should essentially cede its current space where OCaml, F# are, and put more emphasis on pure functional programming. Scala has higher kind of types, and it has 4 expressions, so it has some of the ingredients for that. So, that goes under functional Scala, which is actually a misnomer, I think. Monadic Scala, or as some people jokingly use the name Hascallator as the stairs leading to Haskell. But I really think what this is it's really staged imperative programming through effect systems. So essentially you use a functional programming to construct an effectful program, and that effectful program you know nothing about. It's defined in some library according to the laws of some library. So it's really not a big mystery, and not a big deal. And when people say this is functional Scala, then I think it's a gross misnomer. It's staged imperative programming. So they think we should move to the right towards Haskell. On the other hand, what I believe is that the benefits of functional programming are, there's a law of diminishing returns for them, like for almost everybody else. So some promoters claim that the purer you are, the more utility you will get. I think it levels off somewhere And depending on where you are, it might even drop off if you push it too far. So I have given another talk at the Scala Symposium where I backed that up with code examples. We don't have time for that, so you just have to take me at my word here to say, well, that's where I believe we have essentially the local optimum, and that's also where Scala more or less is. It was designed that way. You could say, well, okay, for an ideal programmer audience, that might be the case. There are diminishing returns. We want to find the local optimum. Here we are, case closed. The problem is that we don't usually have ideal programmers. In fact, if you look at industry, then most people say, well, working in a team is terrible. Well, the people who wrote my code before that I now have to maintain were idiots. And all I need is essentially ways to constrain other people, that they don't do terribly stupid things, industry things like that. So essentially, expressiveness, power counts for nothing. Constraints, rigidity is more important. Cookie cutter recipes is the things that people want. So here the problem is that if you use vars and other effects responsibly, we can make the code cleaner and more performant at some point. But how do we ensure they are used responsibly? How don't we open the gates to the floodgates that essentially people will do whatever and our code will become very hard to maintain? We could think of code reviews, definitely, but sometimes things do slip through. We could think of tests, but some of the problems that arise are essentially data races or leaking references or things like that. And these are very, very hard to find with tests. So typically, Scala programmers, they like the guardrails. And that means we are faced with an uneasy choice. We can say, well, we want to be simple in the language, no fancy effect systems, and also performant, but unsafe. Or we want to be safe, but complex and slow. And that brings me to another thing, that the languages are sort of like tutors or gentle guidance for programmers. So since when I started Scala, I thought I give full responsibility to programmers. They know what they do, maximum power. That was my biggest shift the last 20 years, to say, no. Programmers will abuse absolutely everything you give them. So we need to, and we can't prevent them, but we need to find languages that give them good guidance. And here for effects, there's also a problem in that a program that, ideally, a program that looks simple on the surface should also be safe and predictable. So that means my guidance is essentially shortness and clarity of code, and that means if I do that, then my program will become better. So that's essentially what we would like. But with effects, that's not always the case, because using effects can make programs shorter. Let me just put in this var in here and not essentially thread through this value through a mountains of options and other monadic constructs. But then it would also make it harder to reason about. So essentially, you have the easy thing, which in the end is actually not so good. And that means that a lot of Scala programmers actually shun effects whatsoever. They say, no, you shouldn't use a var ever, because you can misuse it that way. And that means that some vars are inherently evil, what those people say, and you should do pure functional programming. And so the answer here would be a staged architecture for effects, where you say, in the first stage, we have a pure functional program that describes a usually monadic computation, and in the second stage, we execute the effects in the chosen monads. So there are quite a few very popular systems in Scala. So one is Katz effect, the other is Zio, and they all work essentially like this. You have this pure functional program that constructs a program that essentially then has access to all the capabilities of a computer, error handling, file system, network, and whatever. But it means that essentially at that stage it's free for all. So there are no more, essentially the constraints you get, the assurances you get are the assurances of the library, which library authors like. They can design what they want, but maybe users in the language are disadvantaged, because I think as a language designer and compiler writer, you can do more than as a library writer. So the white thing is what programs can do, and then the blue thing is what computers can do, and they do it essentially indirectly by constructing a program. So the problems with this monadic approach to effect system, in my opinion, is first, it's quite a big notational overhead. You have to do these for expressions or do things in Haskell everywhere. And the other thing is, and I think that's a deeper one, that monads don't compose. So monads themselves don't compose, so we have invented a lot of other techniques that work better, monad transformers, finary tagless, MPL freer monads, and so on and so on. So I have the impression every year or two there's another new kid on the block. We say, well, we finally solved this problem, but it gets never solved. The problem gets just pushed around, and this is essentially, it's always a problem to deal with these things. The other approach, which actually in industry seems to be more successful, is the God monad approach. So we put everything in a single monad that essentially handles everything that you should ever need. So XIII is a popular library that uses that approach. And the problem with that is XIII has 3 type parameters for everything. So every program you start with has 3 type parameters for, what is it, environment, error, and result. And that can lead to over-provisioning. Sometimes I don't need an environment. Sometimes I want to do my own error handling and things like that. So it forces you into a framework that if applications fit that framework, it works well. And typically industrial programmers like guidance. They like essentially a fixed way to do things, but many programs don't fit into that framework. So the industry experience with this so far, I think, has been mixed. So what's the alternative? So one alternative would be to say, we want to, instead of, what we see so far is we have essentially languages that some of them are more functional, more lambda-like, and others are essentially more effectful, like C, C++. So those are languages where everything you do, every statement has a side effect, and nothing can return ever. So the other dimension here, which is interesting, is to say, well, can we do compile time tracking of these effects? So here we have languages with a lot of low-level effects. Up there, functional languages with few. And the tracking thing has gained popularity recently, in particular with Rust. So Rust is a fairly low-level language in the fact that it has lots and lots of effects, that it exposes them, but they are finely tracked. So the question, of course, is to say, well, can we do something like this up here? What would be different up here? Well, there would be fewer effects. Our programs would be more predominantly functional. We would minimize effects to the absolutely necessary. And hopefully we would essentially be more abstract. In particular, what we want to do is we really want to get away from this idea in Rust that we have to control the lifetime of every piece of memory we look at. So we want to say, well, no, garbage collectors, they're actually good garbage collectors, help us write concise codes, and in many situations we don't need, we don't care about the performance overhead, which often doesn't exist anyway. But of course we want to be able to escape when a garbage collector turns out to be a problem. Then locally we want to maybe use a different allocation. And over the last 20 years there has been lots and lots of research on this thing. So I just give some research areas, research projects, singularity, mezzo, were research projects, alias types, algebraic effects, linear Haskell. A lot of stuff has been happening there, but it's probably fair to say that none of that is sort of in widespread adoption yet. So here we have our own entry in the field, which is called Caprese, and Caprese is a abbreviation, acronym for Capabilities for Resources and Effects. So that's a large Swiss National Fund project that just started this year in May and will go for the next 5 years. And I'm essentially giving this talk to essentially tell you what it is about and where we are with it. So Caprese means Capabilities for Resources and Effects, and it turns out that capabilities provide safe typing for both resources and effects. Capabilities in that thing, they're simply values in the object capability sense. So I pass a value to it, an unforgeable value, then you have the capability. For ergonomics in Scala, they are passed as implicitly passed values. We have this nice implicits mechanism that avoids all the craft of essentially passing these things explicitly, and that makes them actually workable and quite nice to use. There's still a big question to say, well, capabilities are things that I give you, but you might hang on to them. I might say, okay, now I have the capability, now let me keep that for the next stage, and that we have to track in a type system, as it turns out. That's actually an important difference, whether I take a capability to do an effect now, or whether I store the capability to have an effect in the future, and the type system needs to do that. So with capabilities, we can get to a different architecture where now essentially we are no longer a stage program. We are a single stage program. We can access the whole computer by our program, but each of these things is guarded by a capability, which is the key. So that's essentially there's essentially a difference in outlook for the previous system. Yeah, this one here. The previous system says, well, my philosophy is computers are defined by the lambda calculus. That's what my program can do. And all this thing is magic. We construct a program that then is done by a library that does certain things simply. Whereas here, the new philosophy is to say, no, programs can do everything that computers can do. So all these effectful things the program can do, but we need essentially protection. We need to essentially moderate these things with capabilities. You can do it only if you have the capability. Okay. So what kind of effects are worth with typing here? So important things, I believe, are data races, use after free or close, unhandled exceptions, and there's several more. But I think there's another question. It's a more philosophical question. We want types to reflect and constrain the possible behaviors of our program. So we do not want large classes of problematic behaviors to fly under the radar. Even if you say, well, you can debate the question of checked versus unchecked exceptions. There are good arguments on both sides. In the end, you want to have a mechanism where you can do it when you care about it. A lot of people care about that anyway. So to encourage good code, ideally, we would have encapsulated effects that are easy to declare, whereas global effects should be hard. So to have essentially a type system that gives us a good guidance for programs, we want to say, well, if you just put a local variable or two local variables because they're clearer than a fold or something like that, that shouldn't be a problem. The function is still essentially a pure function on the outside. Whereas if I have a global variable or a field and some globally accessible object that somehow does magic in my program, that should cost quite a lot. And capabilities can enforce that because locally used capabilities are free, there's nothing to pass, whereas a global resource has to be threaded through everywhere in the types. So they have this promise to say, well, essentially my types reflect sort of the difficulty of my program. If my program is hard to reason about, my types should reflect that in also being somewhat nasty. And if my types should be very simple, then there should be a high correlation with programs that are simple to reason about. So hopefully we can get soon to a state where shorter and clearer programs also tend to be safe, and we trust the type checker to guide us to produce good code. That's essentially the reason, the motivation why we are interested in doing this, in adding effects. Okay, so what makes capabilities different from previous work? I mean, there's a bunch of works. Why don't we just pick something off the shelf? Well, the answer is, well, what should we pick? None of that looks that appealing to it. The difference with capabilities mostly is that they are at first just a mechanism, not a policy. So a capability is just a way you can express certain things, and that way works really well with functional programming. So there's nothing that detracts. It's completely compatible with functional programming. Whereas otherwise we would have to start using policy. For instance, ownership type system, we would have to say, well, there's an ownership role which lambda calculus knows nothing about. It's completely foreign to that. Or we would have to talk about move semantics. Again, lambda calculus doesn't care about move semantics. So we would have to essentially lead with imperative things from the start. In the end, we'll have to get there. If we want to express effects, we'll have to eventually get to these things, ownership and move semantics. But the nice thing about capabilities is that at the start, I leave that completely open. It's just a mechanism to describe what is there. So once we can track capabilities, we can add various policies to enforce lifetimes, prevent data races, and so on. That's the approach. Also, I'm going to show you, it turns out that in the end, these capabilities are super lightweight to define and have very, very low notational overhead compared to some of the other approaches that we see. Okay, so there's one other aspect to it, which is very interesting right now, and that's about control effects. So it's not only about capabilities and effects are not only about preventing bad code, but also about enabling new control patterns. So the patterns that we are looking at is result with question mark for errors, generators for iterations, futures with a weight for async. And all these things are direct style, so no monadic composition, but the effects are done directly. So that gives us an intriguing new take on reactive systems, and that's made possible by essentially the recent development in coroutines and continuations that are becoming now much more widespread. So on the JVM, we now have Project Loom, which is essentially virtual threads coroutines. On Scala Native, we have full-blown delimited continuations. And with these things, we can do really interesting things. So what I believe in the end, what Scala should become over the next years is essentially it should stay in this predominantly but not 100% functional segment of languages, but it should expand the footprint of what can be typed well to resources and effects. Good, so that was my overview talk. I have another talk, which for technical reason is in LaTeX, not in PowerPoint. So let me switch to that. It was not at the beginning. Yep. Okay. Okay. No, didn't show. Why does it not show? Let me see. Okay, that's better. Okay. Let me just run this once more through the thing, because I noted that I might have not have done the latest. Okay. Okay, now we fixed the typo. Okay, so as I said, the project is about capabilities for resources and effects, and of course there has been lots and lots of work on both resources and effects, and some adoption is now also starting, in particular the development around Rust is very, very encouraging, but I think it's fair to say that the mainstream is not yet touched very much. So the challenge with all that, and I think that's a challenge that Rust is already facing, is that the notation really needs to be simple and intuitive. And I think Rust is already pushing against its complexity budget there at some point. And for instance, if you look at essentially Rust futures and async, then a lot of people are unhappy with that because they think that that exceeded the complexity budget that people are willing to pay. So we mostly have overspent our typing budgets already, and that's not just Rust, that's basically all typing languages, typed languages that essentially already have type systems that are fairly complex, and the challenge is not to make that even more complicated by talking about resources and effects. So our approach is, as I said, that they can be expressed as capabilities, and capabilities can be tracked ergonomically in types. So when I talk about resources and effects, what do I mean? Well, resources are values, that are available only with certain restrictions. So you can't use the value as you want, whenever you want. Examples of restrictions are lifetime, sharing. You can only use this, only one thread can use it at a time. Quantity, that would be a linear type system where you can only have a single value, things like that. So examples are regions of memory, file handles, channels, database or network connections, and many others more. What's an effect? Well, an effect is an aspect of the computation beyond the shape of simple input and output of a function that we also want to track in types. So an effect is something that essentially an aspect, it's a thing tracked in a type that goes beyond simple parameters and results of functions. So examples are accessing mutable state, throwing exceptions, I/O, suspending a computation, using a continuation for control operations, and so on. And the problem with effects is that they are transitive, which leads to the effect polymorphism problem. So unlike other types, for effects, you have this transitivity property, which says that if you have a calling chain from F1 to Fn, and Fn does an effect, then that's indirectly also an effect of F1. Normally types are local, so if I return an option, then somebody else takes it apart, and nobody needs to know about it anymore. But typically with effects, we're transitive. They go up all the way to the call chain. And the problem is that if this call graph is dynamic, which is the usual thing with using high-order functions or virtual dispatch, then we have this effect polymorphism problem because we can't really, it becomes very difficult to describe the effect of the first function, F1, depending on essentially what other functions it calls. Okay, so capabilities are a way to encode effects. If you don't know that already, here's a simple analogy. So if I have a function f, I can declare that the function returns a type t, and it also throws an exception e, and that's clearly an effect declaration. It says the function has an effect. It throws that exception. Or I can write the function like this. I say the function takes the parameter of type can throw e, that's a capability, and it returns simply a t. And in a way, these things say exactly the same thing. In one way, you say, well, you need the capability, but you return just the t, and in the other way, I say it returns a t, and it might also throw an exception. This using thing is SCALA3 syntax for implicit parameters. So we don't need to name them. We can just pass them like that. Okay. We can also do this, the analogy even holds in a more fine-grained way. We can expand it to 4 steps. The first thing is t throws e. That's actually in Scala simply an infix type. So that's just syntax for throws te. That's a type with 2 parameters, a type, result type, and an exception. So it's and if we look up what throws is, it's a type alias for a context function type. The context function means that it's a function from can throw e to t, but that function takes its arguments again implicitly. That means the compiler will synthesize the arguments. So it's a context function type. So if we expand that, it becomes that. And that function type is essentially by just shifting things where the dot is from function to method. It's the same thing here. It's just the using thing. So you see there's actually an almost mechanical translation from one to the other things, and that the mechanics, the foundations of the mechanics were described in the Simplicity paper, Popper 2018. Okay, so yeah, good. So I can express effects as capabilities, but why should I do that? What's the benefit? What do I gain with that? Well, the benefit is that capabilities support effect polymorphism. To see why, look at essentially our paradigmatic function for everything is sort of like E. coli in biology, the map function on lists in this case. So here's map in Scala. We take a function from A to B. The list is of elements A, and it returns a list of B. If we wanted to add traditional effects to the function, we'd end up with something like that, more or less. So we need an additional parameter E for the effect. Then we say, well, it returns a B and it has this effect E, whatever the F thing is. and then the map function would return a list of V, and it would have the same effect, E. Okay, so, and the problem with that, this might look okay, but it really isn't. The problem with that, of course, is that we have doubled the number of type parameters here, and the other problem with that is that this is really, really widespread. So map, you could say, well, if it was just for map and some other higher order functions, I could maybe work around it. But consider in an object-oriented language, every call is essentially a virtual method call. So no call that I do, well, most calls that I do, I don't know what the target is. So for most talks that I do, I have to do a construct like that. So that would mean I really get a huge number of essentially all these effect parameters of all the things that I call that I have then to assemble back. Another proof point why this is really unworkable is this is actually what Java allows you if you write here instead of F you write what is it, throws, I think. So checked exceptions actually can be polymorphic that way. Only nobody ever uses it because nobody even knows about it because it's just too cumbersome to do. People use monomorphic exceptions in Java. They never abstract with a type parameter over it. Okay, so how do capabilities help? Well, if you write the thing in capabilities, then actually nothing changes. Map is exactly the same as it was before. It's just the function from A to B and this to B. You can say, no, that can't work. I mean, how can you do something that new that essentially that you haven't covered before? Well, the secret is that this double arrow type is now the type of impure functions that can capture any capability as a free variable. So that's how you do it. Since we now all function arrows are impure, it makes sense to also introduce a function arrow for pure functions that can't capture any capabilities. So that would be the single arrow for pure functions in future Scala, in the Scala that implements that thing. So you could say, well, Scala was, we were incredibly far-sighted with Scala 20 years ago. When we introduced it, we used the double arrow because we knew our functions would eventually end up being impure, and we wanted to reserve the single arrow for the nice functions that you know from Haskell. Well, that's just serendipity, I guess. Okay, so let's see how that would work then, actually, in a context where we use a map. So I just say my effect domains is exceptions, because everybody knows about exceptions. So exceptions are not necessarily an ideal effect domain, but everybody knows about them, so let's use them. So what we have is an exception too large, and we have a function that does some computation, and if the input is less than a limit, it is greater or equal to a limit, we throw the exception too large. And what we then want to do is we want to map that function over a list of ints and sum it at the end. We want to catch the too large case and just return -1. So what the system would do with it is this. So it would say, okay, every throws becomes a using can throw. So we have this using can throw here, and it just returns an int. So it can throw the too large because it has the capability to do so. So that's fine. So we have to generate that capability at some point. That's what the compiler will do here. It passes the can throw to the function f. And why can the compiler generate the capability? Well, because the exception is caught. So that's essentially one part where we essentially do enrich the meaning of the try to say, if you catch an exception in a try, then we can generate the capability to throw that exception. Okay, and the trick with the map now is, so this can throw here, this capability, where does it end up? It ends up in the closure of f. So f is a function value, and it takes a parameter x, but that thing will end up in its closure conversion, right? That will be a free variable in the function that will end up here. And because it ends up in the closure, the map doesn't need to know about it. The capability tunnels through. The capability goes, the f holds on to the capability. The map just says, well, I return whatever I have, but we still know that the whole thing will essentially throw that exception because we have to generate the capability here. Okay, and that's why it works. So essentially it's this closure property of capabilities, that things can close over things, which means we don't have to talk about them polymorphically in types. That all happens essentially under the cover. That's the brilliance of it. That's essentially the secret sauce why these capabilities work for effect polymorphism. But of course, nothing comes for free. There's no free lunch, so there's a price to pay. So what's the price? The price is that, let's look at this slightly modified program. So instead of having just a map over a list, I do create an iterator from the list that lazily steps through the list, and I map that iterator. And I put that in a try-catch as before, and then I do next on the iterator outside of the try. So the result of that will be an unhandled exception, a too large exception which is unhandled because, well, what this thing will do is it returns another iterator, and the iterator gets essentially the next function gets invoked outside of the try. So when the next function gets invoked, the function f will be called. But at that point, the try is out of scope, so we can't handle it anymore. So we could either, of course, change our semantics of the try to be sort of capability safe, to essentially stay on, but that would be very, very complicated, and I don't really know what that would mean. Or we have to prevent this case somehow. And to prevent this case, we need to track in the type which capabilities can be captured by its instances. That's the idea. Okay, so let's do a simpler example to see it more clearly. Here we have a simple try with resources pattern. It's a function using log file. It takes an operation that takes a file output string, that's the log file, and returns some type t, we don't care which. And using log file is just a wrapper around it that will create a log file, pass it to the operation, close the log file, and return the result of the operation. So it's a typical try with resources pattern, but it exhibits the same problem as before, that op might return a closure that accesses log file after it is closed, later on when we do that. So it has the same safety problem as a try catch. And what we do here in the type system is we declare that find output string as a capability. And that's done, oops, sorry. And that's done with this simple caret at the end. Caret means, well, it can refer to anything. It can refer to whatever capability. And if you do that, then this usage here would be ruled out. So that's a illegal use, of course, because we do, again, xs.iterator map, and then we do a file write later on. And the error message we would get is local reference f leaks into outer scope of type parameter t of method using log file. So essentially that's where the type system catches us and say, you can't do that. Okay, on the other hand, we still allow this. We still allow a simple xs.map, because at that point, all the writes are done. By the end, we reach the result. So that's okay. And to achieve this, it turns out we need a few annotations on iterator in the standard library, and no annotations at all on lists. So that's essentially the big gain that we get so far with very, very little changes to standard types. And okay, I'm going to show you exactly what they look like later on in the talk. Okay, so before we get there, just some of the technical basics. So what we introduce is these capturing types, which are written a t and then a caret and then a set of capabilities, which are the capabilities captured by the type retained in its environment. And what is a capability? Well, a capability is just a parameter or a local variable. So if we would leave it as that, we would end up with a type system that tracks all free variables of closures, which is also by itself interesting, but probably not for a source level front-end language, because it's too fine-grained. Too much would break. Every little change when we added another free variable would change our type. So we don't want that. So we need to restrict the meaning of what a capability is somewhat more. It's not any parameter or local variable, but it's one of these that has as a type a a capturing type with a non-empty capture set. So it's sort of meta-circular here. You say you are a capability if you capture something which is another capability. Every capability you have to get from some other more sweeping capability. And indeed, there must be a root capability from which ultimately all others are derived, which is called cap, simply cap, in our system. So every capability gets its authority from some other more sweeping capability, which it captures, and in the end you have this root. So I think this is probably the first type systematic account of the object capability model, in the sense that it also tracks retained types and not just parameters that you pass down. Okay, so the syntax of the core, of the smallest core of our language, the simply type lambda calculus variant, is this one here. So it's just essentially a simply type lambda calculus within a monadic normal form, or actually A and F, and technically it's monadic normal form in that we have a let and the lets can be nested. The other thing that's notable about it is that the function type is variable dependent, so we write it with an x here because the x is a local parameter that could serve as a capability. So the capabilities themselves, they are retained in these capturing types here. So that makes technically our calculus a dependently typed lambda calculus, but it's a very mild form of dependency in that the only thing we can track is variables, not full terms. It's actually exactly what Scala does already, so it's a very good fit for Scala because with the dot and the type members, we have basically exactly the same kind of variable dependencies. So you could say this thing really works well for Scala because there are two things you need. You need these variable dependencies and you need implicits to pass the capabilities, and Scala has both of them. So that's why I think it's really a good fit for that. Okay. So what we need then is a sub-capturing relation. So Scala has subtyping. How does subtyping relate to capabilities? So essentially what you say is subtyping is influenced by sub-capturing. So if you have two types, and let's say the type part is the same, but they capture different capabilities, then there should be a comparison between the two capability sets. In principle, pure means no capabilities should be a subtype of all the other types. So the more capabilities you capture, the bigger your types become, and if you can capture anything at all, then you're at the top of the capability lattice. So sub-capturing is simply defined by the subset axioms plus this one, which is very important. This one gives you essentially a refinement, which says, well, we have X here, and it's a capability, it captures something, then that capability by itself also sub-captures the things it derives from. So it means derived capabilities are subtypes, sub-captures of the capabilities that give the derived capabilities their authority. Okay. And that means also that if we instantiate in that rule the C to the empty set, then what we see here is that if X is not a capability, so its capture set is empty, then indeed the capture set X is a subcapture of the empty set by that rule, and that's essentially the rule that justifies that we can simply drop all free variables that are not capabilities. So that's what makes it work, that only capability variables are tracked in these sets. If we now look at the simple typing rules, and there's actually not much to it. So the var rule here, the change in the var rule, all changes are underlined in gray, says, well, if we capture something in a variable, then instead of talking about the captured set, we talk about X itself. By the rule that I showed you before, X is actually better than the capture set. So we improve the type, and that's important because essentially that means we have sharper types. What about the abstraction? So for lambda abstraction, the captured set is, now that's a link with the free variables. So it's the free variables of T without, of course, the bound variable X. So we take that and say, well, that's the capture set. That's all free variables, but of course, by subcapturing, we can prune that to those variables that actually only matter for the capabilities. And finally, the capture set of a closure gets discarded in the application rule, because once we apply the closure, we don't need to, the capabilities are not retained any longer. And that's it. There's really not much to it. But of course, and that's the problem usually in these things, and in this particular case also, is polymorphism. And we have grappled a long time with that, and we have several different solutions. And the last solution we're quite convinced that that's actually the one that works well. So the issue is we could, if you look at the syntax. So the question is, these capturing types, are they essentially a form of full type, or are they separate? And so it's sort of the difference between System F and Hindley-Milner. Do you have a flat type structure, or do you have a nested structure where certain things are only available for certain types? And the issue here is, in particular, once we add type variables. So type variables are certainly a shape type, so they're up here. Can essentially type variables also be a full type? So essentially, can they replace capability types? And if we do that and think it through, then it turns out that means that type variables would contribute to capture sets. So a capture set could now contain not just term variables, parameters, but also type variables, because type variables can get instantiated to these things, and that means we have to track them. And we had a design, and we pursued that for a while, but it turned out that this really gives nastily large capture sets for simple operations. So for instance, if I do just construct a pair of things, so pair is generic, then I have to essentially keep the pair constructor has to say, well, I return essentially my two type variables possibly in the result, and all generic operations would have to do that. So what we did instead in the end, which turned out to be much, much nicer, is to say type variables are shape types, and in that case we need an additional box operator so that type variables can be instantiated with box capturing types. So if a type variable is a shape type, it means it must be pure, no capture set allowed, but you can essentially have a full type with a capture set, and then you box it, which means essentially that the capture set is hidden in the box. And that means you have a pure type that you can pass around, and then you need a separate unbox operation that opens it again. So it turns out that this choice gave much smaller capture sets and doesn't lose much in expressiveness, and further that all this boxing, unboxing infrastructure can be completely inferred. So this is essentially all underneath in the system. So we picked that version, and that will be in an upcoming paper in Toplas and Popper 2024 with that system. So I won't go into a lot more details about this, because this talk is about what we do in Scala for capture tracking. But just as a reference, if you want to find out more, then that's in the paper. And also sort of just as a link, typically if you assess a system for these resources or things like that, then the critical point is always polymorphism, so generics. So that's the one. And the typical way to get out of it, but it's also a problematic way, is to say monomorphize and check after, because polymorphism is gone. But then, of course, you have the problem that essentially errors might manifest in user levels that really have their sources deep in some library. So if you don't want to do that, then you have to invent something else, and that's where typically things get hard. And we're quite happy with the boxing solution that we found. Okay, so what we have then, we have this core type system. We have to extend it to objects and classes and all this, and that's essentially done without, we still need a formal theory for that, so that's ongoing work, but we have it in the capture checker. So we have a capture checker in the Scala compiler that's implemented as an additional compiler parse after typing, sort of similar to the borrow checker in Rust. So borrow checker is also a separate phase. So it's the capture checker. So what we do is we take the whole program and we decorate all inferred types with capture set variables. So essentially we say, well, because we don't know what the capture set part of it, we checked without capture sets before. Let's essentially add a capture set variable on each type that we infer. And then we just recheck the program with the usual typing rules. But it's much simpler now because we have already done all type inference and implicit search and overloading resolution, and all these things are gone. So all we need to do is really the core typing rules, which is about 400 lines of code or something like that. The core Scala type checker for essentially the rules after type inference. So we do that. We recheck the program, and in rechecking, we generate subcapturing constraints on these capture sets that we have added. And we solve those constraints incrementally using propagation. So it's sort of, it's a global constraint solver in that sense, similar to Hindley-Milner, but where Hindley-Milner uses unification, we use subtyping as usual, and that leads us to these subcapturing constraints on the capture sets. The most tricky aspect was to handle type maps. So in this type checker, there are various maps on types. So for instance, there's this famous as seen from map, which regulates how the type of a member of a class changes when you see it from a certain qualifier prefix. There are avoidance maps, which say that you cannot use certain types outside the scope where they're defined, so you have to widen to something else. And then finally, there are substitutions of parameters to arguments. So all these type maps have to be handled in the capture checker as well. And that means the way we do that is we classify those type maps into bijective and idempotent, and essentially have a specialized treatment for each kind of maps. And bijective is sound incomplete, and idempotent is only sound. That means we might lose some precision, but in practice it seems to work out. And then for the box and unbox operations, they can be inferred based on the actual and expected types, similar to the way the type checker inserts implicit conversions. So what we've done so far is that we actually capture checked the .d compiler itself. So we added that for essentially a very specific kind of effect. .d compiler has contexts everywhere. It's an almost pure functional compiler, so everything needs to know. It gets passed in a context, and contexts get sort of updated functionally, so they're sort of a tree of things. And a lot of them generated millions per second, and they're fairly large, a couple hundred bytes. So the idea was to use arena allocation for these contexts and see what happens. Turned out notationally the capture checking overhead was okay, was quite reasonable because the compiler is already fairly functional, so not so many side effects in there, and side effects are quite localized. But the gains were actually less than expected because essentially that had to do with the way we essentially treated the arena allocation. So essentially we pushed the copying around a little bit, but in the end it didn't help so much. We gained a couple percentage points, which actually is very hard to get in a Scala compiler, but still we haven't actually merged that until this stage because it wasn't clear that the gains were big enough. Then the other thing that we're currently doing is port the standard library. That's of course necessary for anyone to use this in real production. You need to be able to use the standard library, and that means you need to know that an iterator captures things, but a list doesn't. So that means that these things have to be captured annotated. So that's ongoing, and that caused us to rethink our encapsulation policy. So as I said previously, capture tracking doesn't really come with a fixed policy. You can add them. The previous policy had to do with boxing, and the new one had to do with this sealed. If you have looked at a very attentive reader, then there was a sealed on a type variable. So essentially we say certain type variables are sealed, and that means they don't let you escape things, whereas other type variables are okay. Okay, and then we are also working on a new stack for direct style continuation-based concurrency and I/O, and that's also ongoing work. So in practice, the annotation overhead actually has turned out to be very reasonable. So to show you that is here's the just an excerpt of list of the standard library. List itself is more complicated, of course, much bigger, more than 1,000 lines of implementations. But that's sort of the thing that shows the illustrated, that shows what changes. So what actually does change is actually quite tiny. I think those are the two changes here. And we wouldn't even need them because essentially what that thing says is a flat map takes an A and it gives you an iterable once of B. And we say, and by the way, this iterable once also can hang on to any capability that it chooses to. If we had dropped the arrow, then only pure iterable ones would have worked. But here we say, no, it's okay. The result of a flat map can, when you iterate it, have effects on its own. So that gives us a more general type for flat map. And the same thing for where we say the thing that we add to a collection, to a list, can be, for instance, an iterator. So iterators are iterable ones, and any sort of collections is iterable ones. And the iterator could have a side effect. So it's probably not good style to have an iterator with a side effect and append it to a list when the side effect will be executed when you append it, but it's permissible, so we can allow that. So by contrast, let's look at the API of iterators. So the first thing is again as it was, and here then there are the following changes now that we say, okay, so for a map of an iterator, we say, well, we return a new iterator, but it will hang on to the existing iterator and also to the function f, which can be a side effecting function, double arrow here. So that's what we need here. And the same thing for flat map, this and f, and the same thing for where we say it hangs on to both the current iterator and the iterable ones that we append to the iterator. Both of it will hang on to both of these things. I think the point I want to make is that to say these are actually useful annotations. These are quite intuitive to say, well, it's actually good to know what an iterator will hang on to, because essentially these are possible delayed effects. So I value in my type system that I know about these things. This is not a nuisance where I say, well, I have to invent lots of polymorphism and type parameters for these things, which are sort of all boilerplate cranky thing. No, these are very specific information that is also useful. Okay, last chapter, we still have a little bit, or yeah, okay, is about control, direct style control. And that's something that has been very, has had sort of revival. I mean, delimited continuations are, of course, very old, but it's sort of that industry is finally waking up to them in the form of essentially green threads or fibers, or sometimes they go for the real thing, which is continuations. So examples are coroutines, of course, existed for a number of years now, and Loom has now finally shipped in the latest Java. Loom is essentially virtual threads of fibers, coroutines, stackful coroutines in Java. Kotlin coroutines, which are stacked-less coroutines. Camel or Haskell, we have limited continuations, and then there's also increasing interest in research languages like Effect or Coca. And I believe that this is about to influence libraries and frameworks, and it's about to essentially shift the focus more or less away from the previous monadic effect frameworks to that. So I think that really is a very promising development, very promising future that might happen in the industry. So what we're doing in Scala is we want to build a low-level direct style stack where what we've done is the first thing is just essentially aborts, boundary break. That's it already in the standard library. Then we add error handling on top of that with a sort of Rust-like result and question mark. Then we add suspensions, and that has shipped recently in Scala Native. Suspensions is delimited continuations. Then we are building a concurrency library on top of that, which is called Gears. That's work that's in progress, and Gears will work on both JVM and Scala Native. So where Scala Native uses suspensions, on the JVM we're going to use Loom. And then on top of Gears, we have plans for doing streaming, HTTP client server, and essentially an application stack, a direct style application stack on top of that. So to get started, we do boundary break, and that's actually the reason that was invented is actually due to Jonathan, I think. That sort of started it all. So Jonathan, he sent me a message at some point and said, well, he's teaching Scala, and in Scala 3 we don't have non-local returns anymore. So non-local returns are out. You can You can't return from a closure, you can only return from the body itself. And he said, well, what should I recommend to students using? Well, you can use a tail recursive thing or things like that, but students, they just want to return. And I said, well, that's reasonable, so let's, but we don't want to go back to non-local returns because non-local returns were too confusing. People didn't know it looked like a normal return, and they didn't realize that it's actually something heavier, like an exception was thrown and things like that. So we said, well, let's invent a new construct, which is called boundary and break. So this is what it looks like. So I think it was even the example you gave me, first index, that you said, well, find the first element in a list of elements. So what you want to do is you go through the list, you zip it with the index, and you say, well, if the element is the first part here, then essentially return the index. And the way we can do this, and if you don't find the list, return -1. So you can do that now by essentially wrapping the whole thing in a boundary. This thing is just essentially a function call. So boundary is the argument here is an argument for the function boundary. And in here, we have a break in the boundary. So boundary establishes a boundary and break returns a value from it. Super simple. So here's the stack view. And we say, well, we have a stack, and at some point we declare a boundary, and then we say break x, and that would essentially return to the boundary and with x as the result. So here's how it would be implemented. Essentially the way we do it, we define an object boundary which has an apply method. So that's why we can apply it, we can pass things to it. That's the SCADA idiom. We always have like sequence, list, they're all objects with apply methods. Okay, so what do we pass in the apply method? Well, we pass a context function that takes a label and returns a t. And the label of t is essentially something that essentially accepts a break for the thing. So we have this class label, which is contravariant in t because it accepts values. And then what the break does is it says, okay, so we break with a value. We need a label to which we can return. The type of the break is nothing, which means there's nothing, the computation will stop at this point. And we just, essentially, we throw a break exception with label and value. And that break exception will be handled by the boundary call. So what you see here is to break, you need a label that represents the boundary. So in that sense, a label is a capability that enables you to break. And that's a very common pattern. And it turns out that when I showed you the exception, there's a bit more to it than that. Implementation of break actually produces very efficient code because if the break appears in the same stack frame as its boundary, then we translate that to just a jump. So it's optimally efficient. And otherwise, we use an exception, but a fast exception that doesn't capture the stack traces. So that exception is also reasonably efficient. I think at some point I heard from John Rose from the JVM team about three virtual function calls. That's about the price you pay for one of these. So it's quite reasonable. And we don't need a stack trace. Why? Because we know that the exception will be handled. We have a handler. We don't throw an exception into the void and just keep fingers crossed that it's handled, and then it might crash, and when it crashes, we need to know what happened. Well, I have to qualify that, of course. To be 100% sure, this needs capture checking. That's where capture checking comes in, that is, to make sure that we don't essentially escape something that hangs onto the label when the label is no longer on the stack. That needs capture checking. Okay, so once we have that, we can go on and do error handling. So here's a function that takes a matrix, implemented here as a list of t's, and it gives you the first column of that matrix. But of course, the first column might not exist for some of the rows. So for the first column to exist, every row must be now empty. So we'd have to check that. So here's a way to express that. We say, well, we want to return none if it doesn't work. One of the rows is empty. So to do that, we wrap it in an optional, and we say XSS map head option. Head option gives you the head of the thing wrapped in a sum if it exists, and none if it doesn't. And then we put a dot question mark. So dot question mark essentially strips away the option. If the option is a sum, then that's the value that we return. If it's a none, then it will break to the enclosing optional. Okay, so how is that implemented? Well, actually, it's also pretty simple. So the apply method of optional, so that takes a body, that gives a label. In this case, the label, all I can do with the label is return none, so that would be the type of the label. And it's just boundary of sum of body. So the body says wrap the body in a sum and put it in a boundary. That's all I need to do. So what's the question mark then? So the question mark is a method on option, the extension method syntax. So we say we take an option of t, and we say on an option of t we can do dot question mark. It needs a label of num.type, and it says, well, let's see what the option is. If the option is defined, if it's a sum of x, we return x. If it's not defined, then we break with the none value. That's all we need to do. So, and of course we can do analogous implementations for other result types. There's no magic to it. So for instance, we could do either, and my favorite actually is a Rust-like result, which we have in our own current library that we use in the compiler actually, but we will publish that soon. So the ideal error handling would be based on result plus question mark, similar to Rust, but it works for deep in stacks, which for Scala is very important because a lot of control structures use closures, so you want to return from these closures without, in the same way you return from simple methods. So it's sort of like a super-powered Rust error type. Okay, so that brings me to stage 3, which are the suspensions. So suspensions is simply what if we could store the stack segment and resume it at a later time. So what we want to do is we want to essentially take the stack segment between a boundary and the current point, and we want to essentially move it to the side, suspend it, and restore it at a later time. And that, of course, is the idea of delimited continuations. So our delimited continuation library, we call them suspensions because it's less scary than the delimited continuations. And we call them resume and suspend and not shift and reset, which is utterly frightening for many people. So a suspension is just a thing that you can resume. And there's a suspend operation which takes a body, which takes a suspension, can do something with the suspension, and return an R, and that one needs essentially the label, the boundary. So suspensions are quite powerful because they can express at the same time algebraic effects and monads. So let me explain that a little bit in the end. So here I have a very simple algebraic effect. That's essentially a Python-style generator. The example here I have here is I have generate, and then I have produce. In Python, produce would be yield, and I can essentially go through some control flow, and I can essentially push these things to the generator. Generator is basically the same thing as an iterator with a slightly different API. So each time I produce something, I have one more value in the iterator to iterate through. So a generator is just essentially where an iterator has next and has next, this one has next option. It gives you next option, an option of t. Okay, or here's another thing which is now stackful and therefore a bit more complicated to handle. So we have a tree, an enum, which is a leaf or an inner, and we want to find all the leaves of the tree in a generator. So we say generate, then we recur in the tree. So if the tree is a leaf, then we produce the next leaf value. If it's an inner, then we recur for each of the inner nodes. That's essentially all we need to do here. So if you look at that from the algebraic effect views, then that thing is an effect scope, this generate, and it also defines a handler. And that produces the effect. We produce an effect, the next value that we generate from the tree. Okay, so how would generate then be implemented? So in generate, so we need to write a generator. Generator needs a next option. And we say, well, let's delegate that to another thing called step. So what is step? Step, when called, needs to return an optional value. So here's our old friend boundary again. So we say, okay, so now we need to produce. Okay, so no, I skipped over that. This generator essentially needs a capability, which is this produce of the capability to produce something. So So we need to generate that. And it's a capability, so it's passed as an implicit, so the way to do that in Scala 3 is as a given. So we say, okay, there's a given produce of P, where the produce method is defined like this. So what does the produce method do? It suspends, it takes the suspension, the continuation of the operation where we are. That's the K, that comes out of the suspend. And what it then does is it says, well, the next time you call step, we resume the continuation and go on, right? So that's essentially it. We set the variable step, so here we have a variable to essentially the resumption of that continuation. And at the same time, we return now the current value x from the iterator. Okay, so that's our handler. And then we essentially just pass the handler to body and return that. So if I take a step back, so what we've done is effects are simply methods of effect traits. So like the producer was that. And handlers are implementations of effect traits, which are defined as implicit values, givens typically, and passed as implicit parameters. So the handler can abort as part of the computation. So first, when you call the handler, it's actually called on the call stack of the client. So it's just a function that you call, a virtual function that you pass down. So then that function can choose to abort, that's a break, or it can also choose to essentially just return, do nothing, return, that would be a resume, or finally it can choose to suspend the computation as and resume it later. So that's an interesting approach, and it's slightly different from the more traditional view of algebraic effects, which often gets characterized to say algebraic effects are resumable exceptions. So because in resumable exceptions, essentially somebody throws an exception or raises an effect. Somebody else hopefully handles it. The type system by itself doesn't give you that. But we don't actually know statically which handler. We can declare exceptions, of course, and we know that some handler will capture them, but you can always essentially smuggle a handler into the stack. So you think down there, you throw an exception, and I say, up here I have a handler, and there's some virtual calls in between that I don't know what's in there. One of these virtual calls might contain another handler for your effect, and then it will be that handler that captures it. Very powerful, but also potentially quite scary and unsafe. So I think this is sort of akin to dynamic scoping, really, whereas continuations are really static scoping. Dynamic scoping in the sense that your dynamic call stack can decide what handler actually gets called. Okay, so to implement these suspensions, there are several possibilities. So we've done them for Scala native directly in the runtime. There's some effort to make them work on top of Loom. Jonathan can tell you more about that. It's not always easy going. It seems they have like 95% of the right abstractions, but not 100%, something like that. One could also do bytecode or source rewriting, and we're looking into that. Okay, so the other thing is monads. So we can do these suspensions and continuations can do monads, and that brings us back to a famous pair of papers 20 years ago in 1993. Phil Wadler wrote essentially the seminal paper on monads for imperative programming in Haskell, and he showed that continuations can be expressed as a monad, and somewhat provocatively his paper ends with the statement, so in that sense, Haskell is the essence of ML. Then a year later, Filinsky came back and showed that every monad can be expressed in direct style using just delimited continuations. That was essentially when, around the time when they were maybe not invented, but when people first took notice of delimited continuations. And he, of course, had to end the paper with ML is the essence of Haskell. So we have actually implemented Filinsky's monadic reflection suspensions, and that was last year in the talk at Hope. So to conclude, the capture-checked capabilities have the potential to solve some long-standing problems. I've talked about effect polymorphism, getting flexibility without the overhead. Linked to that is really this what color is your function problem of asynchronous computation, because that's just an effect polymorphism. We want to have the same computation work for sync and async. I haven't talked about resources for allocation, but we have a prototype to do regions in this system for arena allocations, and on top of, together with the garbage collector. And the other exciting area is fearless concurrency, excluding data races and other hazards. And Yichen will have a talk about essentially our thoughts of this later in the workshop. So I think in summary, I think capture checking is particularly good in situations where only a few capabilities need to be tracked. There's this sort of things to say, well, if things are predominantly pure, there's nothing to do. You pay for what you use. You pay for just a few capabilities. So it's really good in mostly functional with few resources to manage, which is essentially precisely the spot Scala is in, and that's why I think it's actually a very good fit for what Scala is, and a very good way to extend it further. So to find out more for capture calculus, the first publication was the Scala Workshop 2021. There's an upcoming top-class Popple paper. For the capture checking prototype and user guide, you can just Google Scala 3 capture checking. There's some user guide material there if you want to, if you feel adventurous and want to use it, but we still have to get the standard library into a capture check thing. So for the moment, it's basically just exploration, but not production use. But hopefully over the next months, we'll be able to ship the standard library in capture check form. And if you want to look at the code, then it's lamp.pfl.dati, the branch where we work. No, it's actually in main, but the pull requests, it's all labeled with CC experiment. So if you want to find out what happens there, then look for that label in the repo. And that's it. That's all I had. Thank you.
So we maybe have time for like 1 or 2 questions.
Yeah, sorry to go a bit, have gone a bit over time.
So do we have someone who wants to ask a question?
Hi. I was kind of curious about how you do the effect handling, and for example, can you support non-determinism and with multiple resumptions? That's known to be interacting very badly with mutable state, and you seem to use mutable state pervasively.
Yeah. So you should ask Jonathan that. He's the expert on these things. Right now, our answer is single shot only. So no non-determinism in that sense, because precisely we haven't figured out how to do mutable state, and the answer might be it's too complicated. We will essentially just limit ourselves to where it's not a problem.
Yeah, people tend to lump all the state onto a big top-level handler, which is kind of not very good design. So this is kind of, I'm very curious how one would solve this in general.
I don't know, but if I look at what actually where we actually need this thing, then I would say 95% is async right now. And if you have a good solution for async, that's what people clamor for, essentially.
Thank you.
Okay, thank you for the question. Another one maybe? Okay, if not, then I don't want to keep everyone waiting because we are already past the end. So thank you again, Martin, for the
Thank you.
Okay, so we have a coffee break now, then we have a number of diverse talks, and I've been informed that there is actually a discussion panel, so we will try to update the schedule as soon as we can, as soon as I find out what the discussion panel is about, and I'll also let you know at the end of the next session. about borrow checking high-low.
Thank you very much. Why I cannot see my presenter notes? This is not good. All right, technology is great. Hello everyone, I'm Zimi. I'm a postdoc at EPFL, but I did most of this work during my stay at Northeastern University. So that's why I mentioned the two institutions. And today I'd like to talk about a programming language I'm developing with amazing people. One of these people is my co-author, Dave Abrams, who happens to be the person behind the Swift standard library. So if you've done any Swift language, you might see some resemblance. It doesn't come from nowhere. So what is Hilo? Hilo is a programming language for high-level systems programming. Think about device driver, 3D rendering engines, or even compilers, right? It is designed to be safe by default, fast by definition, and it has a strong bias toward generic programming. Today, I want only to focus on the two first goals. The generic programming is a whole thing on itself, but yeah, I think with safety and efficiency, our plate is already full. So what do I mean by safety? I think it deserves some definition because safety is a kind of overloaded term in the PL community. So by safety, I mean freedom from undefined behavior. And this is a nice and concise definition, but if you're not from a C or C++ community, maybe it's not that helpful. So let's dig a little deeper with a C++ program. I know C++ is very scary, but don't worry, it's the only example we'll have today. So the first line here is creating a vector. This is a dynamic array. And it's initialized with the French and Japanese translation of hello. And then the next line is getting an iterator on this vector. This is also like a scary term in the C++ community, but just think as kind of a pointer to a part of the vector. And then we call resize. And this method says, I want the vector to have enough storage to contain at least here 10 elements before you need to reallocate storage, but keep everything that you had already. And then we want to dereference the iterator we had to show what's the first element. And now, boom, this program has undefined behavior. The problem is that when we call resize, we might have reallocated new storage, and so it invalidated all pointers we previously had on the vector. So when we try to dereference here the iter we had, we cause undefined behavior. So this looks like a plain old bug. So how bad is it exactly? We know bugs, right? Well, it's really bad, because undefined behavior means that this program can do literally anything, including summoning demons from your nodes. But more seriously, what this program could do is start interpreting data in your program, arbitrary data as code. And so you can open all sorts of security issues with that. So what can we do about these kind of bugs? Well, if you're using a language like C++, basically the only choice you have is to be very careful. But if you're using a safe language like Scala, for instance, we had a very nice presentation about Scala before, then you don't need even to care about that because undefined behavior cannot happen. It's a safe language, and by definition, safe language don't have undefined behavior. So for instance, this is a Java program. It's not as nice as Scala, but still makes my point. This program is a transliteration of the C++ program we had before, and it also has the same bug. But there is a difference. When we execute the last statement here, we have invariably an exception thrown at runtime. And this is much, much, much better, because at least now we kind of reduce the realm of possibilities there is when we write a bug. So we don't need to be so cautious anymore, because at the very least, we have a safety net. And this safety net is very important because, well, even amazing developers make mistakes sometimes. But if safe languages are that great, and they are, well, why C++ is still around, right? Well, the answer is efficiency, and this is the second stated goal of Hilo. When we write a program in C++, it gets compiled directly to machine code, and that's really nice because that means we can very closely describe the operations that we want to apply with great efficiency. That's because we are very close to the real hardware systems that runs our program. And the real hardware system doesn't care about lambdas, right? The real hardware system is just a dumb machine that does mutation on its registers or on its memory. So if with C++, we can write super complicated abstractions, very nice abstractions that we humans like, but we can get the guarantee that they are, they are compiled without loss of efficiency. And that's very important to us. This is in contrast with a language like Java that introduces a middleman in this whole process. When we write a program in Java, it doesn't get compiled to machine code. Instead, we get an intermediate representation that is executed by a virtual machine. And this virtual machine is on top of the actual hardware. So the advantage is that we can rely on this virtual machine to do all sorts of things, like dealing with memory for ourselves. Or it can also make a lot of checks and guarantee safety. So it's very nice, but it also comes at a cost. The first cost is that the middleman introduces a lot of delay, because the middleman is allowed to stop the world at any time to do some sort of operations that it feels it's appropriate. For instance, it may stop the world to reclaim memory. That's the cost of automatic memory collection. And okay, Martin told us that garbage collection is not a problem in practice. Well, I think it is for very specific applications, but even if it's not a problem, you still have other costs that come with the middleman. So for instance, it may also stop the world to try to come up with a more efficient way to run your code. That's just-in-time compilation. And it's often necessary because running bytecode on itself, as it is order of magnitude slower than running native code. So a JIT compiler can get you closer to what you have done when you, if you had written your code directly in C or C++. But you don't want this cost also, because there is warm-up and all sorts of things. Right? And lastly, there is also the problem that the middleman imposes some tax on the abstractions that you want to use. So now when you define abstractions, it's no longer free. For instance, if we define here this vec2, it's kind of a pair here, the allocation of this object in memory uses a lot of boxed objects all over the place, and now if we want to access the elements of these vectors, we have to pay for pointer and directions. And cache locality matters, so this is also costly. Now, to be fair, compilers and JIT compilers, and we have a lot of smart people here working on these dynamic languages. They come up with all sorts of tricks to alleviate these costs using ahead of time compilation or just-in-time compilation of any kind of older code transformations. But none of these code transformations are guaranteed. There are optimizations that, when we are lucky, we have them. So if we want true guarantees about efficiency, we can't use them. The last thing I said I will just briefly mention is generic programming. And one thing I want to make clear is when I talk about generic programming, I just don't mean type polymorphism, right? When I talk about generic programming, I'm borrowing my definition from Alexander Stepanov to mean that it's the practice of writing algorithms in terms of the algebraic properties of the data on which they operate without loss of efficiency. So again, this kind of efficiency comes up here. And so here, I won't get into too much details, but having a difference in the way your data behaves makes this practice a bit harder. All right, so let's address the elephant in the room. I've talked about high-level systems programming. I've talked about efficiency, zero-cost abstraction. I'm sure you're all thinking about Rust, right? And I'm also sure that the entire audience here is kind of familiar with Rust, but just to be sure, let's introduce the language a little. So Rust is a relatively young language that promises safety without loss of efficiency, because unlike Java, it doesn't rely on a virtual machine. Instead, it guarantees safety with kind of a sophisticated type system. So here we're looking at a very simple algorithm. It's not a useful algorithm, it's n squared, but it's just here to illustrate some concepts. This is a function that removes from one vector the elements of another vector. And it's surprisingly difficult to write this function in C++ safely. The problem is that we are using two references for efficiency, and when they are less each other, well, things can go very wrong, like the first example that we saw. But in Rust, because of the nice system of Rust, we don't need to worry that much, because Rust will guarantee that they cannot alias each other, because the first one is mutable, and so if there is a mutable reference, it cannot alias another reference in scope. So we have the guarantee that the safety issue that we would have in C++ cannot happen. In fact, if we try to force the issue, we will get a compile time error. The compiler will say, well, you can't do that because you cannot borrow S as immutable while it is being borrowed mutably somewhere else. But so Rust has very nice error messages. This is great. So it seems like it's a very good approach to a very hard problem, but it comes with cost, right? No free lunch and all of that. Rust is complex to use. It has a steep learning curve, and it's to the point that fighting the borrow checker is kind of a meme in the Rust community. The borrow checker being the part of the language that guarantees all of this stuff, right? So the first issue, I would say, is that first, these notions of references add a lot of noise to the code. If we were looking at this written in Scala, for instance, we wouldn't have to care about these sigils here, the ampersand, the stars, and everything, right? This is all additional costs, like cognitive costs we have to keep around. This is because we are dealing with references, but I claim that usually when we write programs, we don't care about what is a reference or what is a value. We just care about the value. We care about the real deal. We care about what the vector is and what the vector contains. We don't care about whether or not these things are references. The references are mostly there for efficiency. And if you look at how people write C++, for instance, it's very clear. Const reference means pass by value, but efficiently because I don't want to pay for a copy. Very, very clearly. So this is the first issue. And the second issue is that here it doesn't show, but to perform its magic, Rust uses lifetime annotations. And this is kind of a crazy example. Here we have 3 lifetime annotations, right? It's kind of a crazy object. So the first one, buff, is defining the lifetime of some buffer. And the colons say that it must be longer than decoded, which is the other one that represents the lifetime of decoded objects that are projected out of these things. And then we have yet another one that's labeling the decoding objects. Right? It's kind of a crazy example. To be fair, most code doesn't look like that, and lifetime inference is pretty efficient in Rust. We didn't have any on the subtract function earlier, but still, there is some code that needs to rely on this, and this is hard. This is hard to deal with. So even with all the niceties of Rust, the nice error messages and the lesions and all of this stuff, I have yet to meet a Rust developer that doesn't long along when I say Rust lifetimes are a real struggle. And everyone agrees. Okay, so what can we do better? Well, here enters Hilo. I'm shamelessly plugging my language. And Hilo does also the safety thing, but instead of using references, it uses something called mutable value semantics, or MVS for short. And the basic idea of value semantics is that it's bans sharing, it bans sharing mutable states, but not mutation. So you can still do your mutation, your in-place mutation, as in any programming languages, but you cannot share these mutations with aliases. So here, for instance, in this program, we are mutating in place the first part of a pair. And this is like what we would write in C++. That is in contrast with language with reference semantics, in which if you want to guarantee like the independence of values, basically the only thing you can do is functional update. So for instance, in Scala here, we would have to reassign the pair to a brand new pair, and then we use S2 for the remainder of the program. So that works, but first it's kind of it adds some overhead, and it doesn't scale very well for deep data structure. And also now it's pushing a lot of pressure on the optimizer to recover the efficiency we lost with this thing. Because now we allocated a brand new pair just to, well, change the pair we already had. So all of these new objects in memory, we don't want them. And so in Hilo, we can do the in-place thing. So another important feature of the language is that it has a linear type system, meaning that all values must be used exactly once. So linear type systems are great for modeling resources, like memory, for instance, but they are notoriously difficult to use. Here, for instance, this program is actually wrong. If we try to compile it, it will say, the compiler will complain that S was consumed. It was already being used, because when we said var t equal S, we moved S to t. Okay, so this model is great. We can forget about all the issues with references and everything, because basically all values are unique, but it's hard to use. So Hilo has a few tricks up its sleeves to help with this issue. The first is to relax the definition of using. So most of the time when we use a value, we just want to read its content. We don't want to take its ownership and destroy it, right? We just want to see how it looks like. So in Hilo, we can say that instead of taking the value, we just want to pick at it. And so this is a let here instead of a var. A let is kind of an immutable binding to some value, right? And now it's only using to read, and so there is a distinction between using to read and using to consume. So the let binding is just reading S, and so now this program is fine. But what about consumption? Because I said it's a linear type system, and nothing consumes either S or T, actually. So am I lying? Well, the thing is that deinitialization is a kind of consumption, and it's usually inserted by the compiler itself. So the compiler can figure out, you don't need S anymore, we can deinitialize it, and now S behaves like a linear value again. And this is important because that means we can attach behavior to deinitialization. It doesn't have to be just dumb deinitialization. We could do RAII. If you've done some C++, for instance, it's used extensively, we can do cleanup and all of this stuff. So what's nice about this is, well, you don't have a garbage collector, but do you need it, though? Because it's infamous in C++ that you need to manage memory manually. But with this thing, we don't have any new delete or anything, right? It looks like what we could write in Scala. So we get the niceties of garbage collection kind of for free. Of course, no free lunch, and we will see some of the limitations later. So at this point, you might think that T is just as good as a reference, and I said there is no reference in the language, so what am I talking about? Well, it is under the hood, but what's important is that at the language level, at the user level, we don't need to think of these things as being references. They are just values. For all intents and purposes, T is an independent value and I can do anything I would do with a value. And the language will guarantee that this is true. And so if I try to trick the system and do an operation that would violate my assumption, the compiler will catch me. So for instance, here, if I try to modify S while T is extant, then this is a violation of my guarantee, because the guarantee would be T is an independent value. Its value cannot change if I don't mention T in any operation. And now here I've changed T, so this is obviously an error. So here I need to change my program, or maybe do a copy, or rewrite my program in some way. But the hypothesis is that this kind of situation doesn't happen that often, because most of the time we just use values for reading. We can create write accesses too. So here it's an in-out access, the same as the let access we had before, but we are allowed to modify T. And again, T is an independent value for all intents and purposes, and also I'm able to modify it, and so I can write this program. If I try to violate the constraints, again, the compiler catches me and says, well, you can't do that. If you try to print S while T is being mutated, then the independence guarantee of S is violated, so please don't do that. And we can use these passing conventions on functions, and so this would represent, for instance, mutation across function boundaries. So this is actually the only way to do mutation across function boundaries, because we don't have references. So now we are ready to look at subtract again, and we don't have the pesky stars anymore. These things are just values. It's a bit nicer to read, I would claim. Okay, so we can write mutation across function boundaries, but what about accessing the values of a container? This is some Rust code here, and in Rust there is this getMut function. This is a very useful function that gets you a reference to the contents of a map, for instance. You have a hash map, and you want to access the value for a specific key. And this is very useful to have this operation, because let's say you want to just update the value for a specific key, you don't want to pay for 2 hash lookups. And if you were using a pure functional programming language, you would even have to rebuild an entire map, which is crazy expensive, right? So it's very nice to be able to do these things in place. If you don't have references, well, it's a bit hard. So the thing we do with high-low is that we say, well, instead of projecting the reference out, let me just execute the code that you want to do with your reference, right? And so now I keep ownership of all my parts, and I execute the code that you want, and then no one is the wiser. And this is captured by this inversion of control mechanism. So now the only thing we have to do is come up with a nice syntax, because users typically don't want to deal with higher functions all over the place, right? Except if you're a Haskell fan, I guess. So the trick, we took it from Swift. It's a subscript, and now at the call site it looks kind of traditional programming, right? You get a subscript of your map, and then you can do whatever you want with it. But this mechanism is actually even more expressive than the reference one, because we can project anything we want, even values that don't have an actual representation in memory. So for instance, we could say that, let's consider this UI32 is a collection of bits. It's a bit field. And the only thing I need to do is define a subscript that projects booleans. And so now I can yield the value of the boolean, and yield is kind of reminiscent to coroutine because it's exactly that. It's the version of control. The only difference in the subscript is that the subscript has exactly one yield on every code pass. It doesn't yield twice, it doesn't yield 0 times, it yields exactly once. And we can bundle different variants of this subscript. For instance, we can have mutable one, and now we can project a bool out and then get the value back in. And after the yield statement, we have a chance to apply the mutation back to our actual internal representation. So now I can really consider my UI32 to be a collection. And at the call site, again, it looks like traditional programming. So, okay, enough about the language. We're here to talk about compilers and implementations of these aliasing tracking things. So let's talk about the compiler. It has very traditional compilation pipeline, nothing very interesting here. What we want to talk about today is the IR generation phase, and this is where the borrow checking of high-low happens. You might notice that it's not part of type checking. So you might quote me when I say type checking, I don't mean anything to do with the lifetime guarantees or the access of everything. Type checking is just figure out what is an int, what is a string. Then our generation is all about guaranteeing the access rules are satisfied. Okay, so our generation is decomposed in several steps. I don't have a lot of time, so I'll zoom a bit through it. But the first is IR lowering, which is translating this high-low representation into an IR form. And this IR looks kind of like LLVM, so not getting too much into the detail, it's kind of this assembly thing, right? It's not very pretty to look at, but it has nice properties. Basically, it's SSA form, and it's convenient to do analysis and optimizations. We're mostly interested in analysis here. So we have registers, and registers corresponds to the variables of SSA. They are not directly correlated to variables in the language itself. So for instance, %1 is the allocation of the literal that we pass to the subscript, but they might be, this is the case for %8. And we do a lot of stack allocations. It's okay because these allocations will be optimized away by LLVM later on. And this stack allocation can represent the object lifetime of something, right? It's a memory cell, it's not initialized, and then you can put a value in it, it's initialized, and then you can put the value out. So it's easy to track. The initialization is inserted, as I said before. Let's go a bit quickly over these things. And now, what's interesting about this IR is that we have these access operations, which are ghost instructions. They don't have any meaning in the operational semantics, but they can be used by the borrow checker to figure out what's going on with the access. So here we're saying I want a set access on the value, and the set access requires the object to be uninitialized, and so here this is guaranteed by the compiler. Okay, I move a little. Access verification is not the most interesting. Last use analysis is just, we have non-lexical lifetimes like Rust. This is very simple algorithm. We figure out what is the last use of all of these things, and we insert end accesses for everything after the last use. Nothing very interesting. What I want to talk about, a bit over time, I'm very sorry about this, is definite initialization. So definite initialization is a popular static analysis technique, guarantees that every object is initialized before use. We extend this definition in high-low to say is also uninitialized before being deallocated or uninitialized before a set access. And we do that with an abstract interpreter. So the only thing we do is to execute this program in the compiler in an abstract domain that only cares about the initialization state of the object. So we start here, we allocate some stack, and then we track what is the value in memory, and we move as we go. I think you get the idea. And if something goes wrong, we can either try to fix the program by inserting new IR, so this is how the initialization is inserted, or we can report an error. And exclusivity checking is the same thing. It's doing the ownership analysis, if you will. It's guaranteeing that you cannot have two in-out accesses. If we would try to run this program, for instance, we would figure out that it is an error because the state in memory would be something like that. And once we're done with all of these steps, we're ready to co-generate this thing. This is LLVM stuff. We don't have to care about this. LLVM is very good at optimizing this kind of stack heavy code. And okay, that's all I wrote for today. Sorry for going over time. Thank you for your attention. If you have time for questions, I'm ready to take one.
Okay, so we have a time for a few questions. Does anyone want to?
So your definition of safe is a bit loose in the sense that what is your compiler actually guaranteeing? Because just undefined behavior, if you don't catch an exception, doesn't prevent the program to crash, right?
Yeah.
So what exactly is the compiler guaranteeing?
The guarantee is just no undefined behavior. You may crash, and you may try to access an array out of bounds. What you know is that you will crash. You will not run into undefined behavior.
Any other questions?
Hi. I was thinking about this mutable value semantics, and it seems like sort of everything is a value unless you try to observe something that would reveal that it's actually a reference, and then you disallow that. Like, it's a bit philosophical, but isn't it a reference? Then you're just disallowing the things that would make it show to you that it is actually a reference.
Yeah, in a sense, yes. The difference is that the references don't show up in the type system. They are not a user level concept. You cannot store a reference to something. You can only store the value of something. And so, sure, you can think of them as references if you want, but it's as good as just to think there are accesses to values and accesses on which I have certain rights and duties. Because if they were like fully first-class references, then we would enter Rust territory and we would need to track lifetimes and all of these things.
Okay, thanks.
One more question, maybe?
So about the limitations, can you write cyclic data structures?
That's the thing, right? So what about doubly linked lists? So yes, you can. There are a few tricks you can do. Basically, it's the same story as for Rust. You can do reference counting cells, so RC cells, and a lot of people write that in Rust. I think it's not the best approach. The best approach is just to rethink your programs. You can write arbitrary graph structures with adjacency lists. And it might sound foreign, say, oh yeah, it's a step backward, I want my references, but actually, you can write very nice and concise definitions of like graph algorithms using these data structures. So I think it's actually a win if you think more in terms of what is the values that I have. But yeah, this is the obvious limitation.
Okay.
Thank you very
I
much.
think that's all, so we can thank Dimi again. To show your presentation.
Nice. My presentation has my transcript.
I see.
Okay, Windows.
Mm-hmm. Okay. I'm sorry, Adobe just decided to update itself. I didn't know that Macs did this. I thought this is only like Windows that restarts during the middle of the presentation.
Technology is great.
Yes.
Can I see the presentation on the screen too?
I don't think we want to fiddle with that. I mean, okay, can we? Okay, now we need to move it there. Yeah. I'm sorry, I promise we will figure this out a bit better by the next session. Okay, so try to speak to the microphone too. If you need to point, then point with the cursor.
Okay, sure.
Okay. Right. Sorry for that. So the next speaker is Shu, who will be talking about degrees of separation.
Okay. Well, how do I put it?
Sorry.
Yeah. So, hi everyone. Today I'm glad to present our work on degrees of separation, and that work is done in collaboration with my co-author Alexander and my advisor Martin. And so let's talk about our system. So our system is a flexible type system for data race prevention. So before diving into the system, maybe first see what is a data race and how we can use type system to prevent them. Okay. Okay. So what is data race? I think everyone here knows, but I'll explain briefly. So a data race happens when mutable state is accessed concurrently by multiple threads, and at least one of them is mutating it. For instance, in the example here, we spawn two threads, so the two bars is basically running two expressions in parallel. It's a hypothetical syntax, and this is two users. The first one try to acquire one item, and second one try to acquire two items. So this is certainly a data race because the num items is accessed concurrently by these two threads. When such a data race happens, the result of the execution will be non-deterministic. So there can be different results from execution to execution, and there can be undefined behaviors, and there are some important invariants that can be violated. For instance, here we might end up with both users thinking that they have acquired the item, and the remaining item will be negative. So why is data races happening? This is because of aliases. So aliases has been quite a mainstay in a lot of programming languages. As Dimi just said, it can be used to pass values by reference efficiently. And, but there are certainly problems because if we have aliases, one part of code can affect the other seemingly unrelated part, even in another thread, like the data races here. So it is like a spooky action at a distance. So people do want to prevent data races, and they can do that dynamically, for instance, via some synchronization mechanisms, or statically, as we will see using type systems. So previously, a lot of type systems, like mainstream programming languages like C++ or Scala, they doesn't care that much about aliases, and they use aliases a lot. But recently, more and more type systems, they start to paying attention more and more to this problem. For instance, Rust, it supports fearless concurrency, which is its quite famous feature. And if we translate that example directly into Rust, it's the same example. We have a mutable variable that is shared by two threads, and each thread is one user. That will be rejected by Rust because here we are trying to mutate the num items in the two threads, and each thread will mutably borrow that mutable integer. And in Rust, it is disallowed because you can only, a mutable borrow in its lifetime is a unique reference to that mutable state. So yeah, we do have type systems that can prevent data races. And why do we want a flexible type system to do that? So the main principle of a lot of existing systems is better unaliased than sorry. So for instance, for Rust, it can enforce uniqueness. So in the example we just saw, we create a mutable borrow to the num items variable in one thread, and in the other thread, we try to do that again, and that will be disallowed. So the mutable variable cannot be aliased by these two threads and cause data races. So what is the problem of it? Is that So to maintain this uniqueness invariant, Rust not only enforces it on part of the program that can cause data races, but also on the entire program. That is not a bad idea because the uniqueness invariant can offer us much more beyond data races, like compiler optimizations and other memory management optimizations. But this will require entirely a new mindset for programming, because previously we don't have these assumptions about aliases. So this inevitably invalidates some existing programming patterns. For instance, here, this is another Rust example. We have a vector which takes two integers. It's a two-dimensional integer vector. And we have an update function which takes a multiple borrow of a vector and two functions to update these two fields. And in the main function, what we try to do is that we want to increment these two dimensions by one, and at the same time compute the summation of their old two dimensions. And this is a reasonable programming pattern, but of course, Rust won't allow it because basically in the two closures, each of them will multiply borrow the P, and that is disallowed, though they are executed sequentially and no data races can happen. Okay, oops. I'm clicking the wrong button. So we are kind of at a dilemma here. So we have this old mainstream programming language. We don't care that much about aliases, and we use aliases a lot, and a lot of code is written in them. And we have those new languages which can control aliases, but they come with a completely new set of principles and mindset. So we cannot easily migrate these old code bases and the existing programming languages to use these new techniques. So can there be something in between, which we can maybe enjoy the bright side of both worlds? And so let's set some ideals. So for instance, this is the same example, but again, written in some pseudo Scala. And we are updating this vector 2 and compute their summation at the same time. And this should be allowed because these two closures are executed sequentially. But this example should be disallowed. And the only difference between these two examples is that the par update function, it will execute two closures to update the pair in parallel. So the two bars, again, is a hypothetical operator which runs two operations in parallel. And this indeed calls the data race, and the type system should reject it. So here's our objective. We want to have a system that is flexible enough to accommodate those programming patterns while aliases are used a lot. But when needed, it is also capable of controlling aliases when data races is really a concern. And if we can do that, then it would make it easier for existing code bases to be migrated to these new systems and enjoy the safe concurrency guarantees. At the same time, the migration cost won't be infeasible. So now we see that flexibility is important, but how can we do that? Maybe let's rethinking these existing mechanisms. Why are they restrictive? For instance, uniqueness. So we think that because they are enforcing some global aliasing in free environment, and here global means that X being unique, it implies that it is not aliased with anything else in the context. But our intuition is that instead of making such a global invariant, we can let the user to specify the degrees of separation, which means that what a value or a reference is actually separated from. And by default, that degree can be empty, which means that no alias prevention invariant is enforced, and the type system works the same as before. And when there is really a concern about data races, we can properly specify these separation degrees and reject those programs that cause data races. And to this end, we are proposing a calculus called capture separation calculus, which we short-named as CSC. So how do we do that? First of all, how does this update and par update function we just saw look like in CSC? So it looks like the following. First, the update function is unchanged because it is sequential, it doesn't cause data races, and we don't have to do any code refactoring to make it work in the new system. And for the part update function, as you see, we have some new annotations, those SEP annotations, which specifies what we call separation degrees. And technically, every variable binding in our system have a separation degree, but by default, that's empty. And if that's empty, then the system works as if there's no alias controlling. So actually, we have a prototype implementation which supports separation degree inference. So actually, in practice, you don't have to write out the separation degrees, and in most of times, compilers can infer them for you. So, and what does this annotation mean? So this means that SEPPF means that G should be separated from both P and F. And what is separation? It is non-interference in CSC. This means that if both F and G is accessing a mutable state, then both of them are just reading. None of them are mutating the mutable state. And here, the pavo, it denotes a parallel lit binding, while the binding and the body is evaluated in parallel. So its semantics is a bit like futures. So for instance, if we define a pavo A, which is a result of OP1, and we have, again, we define a normal lit binding B, which is a result of OP2, and return them as a tuple, then it could be understood as defining A as a future, and you go on to execute the body, and when A is really needed, it is awaited. So how does separation? So separation checking is another important device in our system, and it can establish the separation between two sets of variables. It is used in two places. First is the function application. So it ensures that declared separation degree, as we just saw, is actually respected. And the second place is parallel lets, as we just see in the previous slide. It will check that the binding and the body, the variables used by the binding and the body should be separated. And this will statically ensure that there is no interference or data races between the parallel evaluation of the two. And this is the essence of how data race freedom is statically ensured in our calculus. So, and maybe let's see an example on separation checking parallel lets. So this function, it is quite familiar. We just saw its body. So it takes two operations. It runs the two operations in parallel and returns their results as a tuple. And when we are type checking the body, the binding term and the body term, the binding term would be just OP1 being called with empty arguments, and the body term would be the rest of the body of the function. And these two will be separation checked, and this will require that OP1 and OP2 are separated, which is true because we have a separation degree annotated for OP2. And how does it work for function applications? There are two examples. The first one, if we want to, so we first assume that A and B are two disjoint, distinct mutable integers, so they won't interfere. And if we want to parallelizing the two operations which incrementing A and B respectively, it will work. What happens is that when we type check the first argument, the separation degree is empty, so it succeeds. So it's like no aliasing controlling is happening. And for the second one, we want the separation between A and B, which is true. And for the second example, we want to incrementing A and at the same time reading A, which is indeed a data race, and it will be rejected because type checking the second argument will require the separation between A and A itself, which is not true in our type system. So how does this separation checking actually works? We are using it, but how does it work? So basically, it's symmetric, and once establishing separation between two sets of variables, we will require the pairwise separation between each variable in the two sets. And how does the separation between two variables established? First, it will make use of separation degrees, as we just see. If OP2 is annotated to be separated from OP1, then this can be accepted. And secondly, it will follow aliases. And this implies that our system has some mechanisms for tracking aliases in the type system. And this is capture calculus we just saw in the morning. So its core concept, which is capturing types, it can be used to track aliases. How it works is that so the shape type, it is ordinary type, and the capture set, it predicts the captured variables of the value of that type, and that one can be seen as the aliases returned by the value. For instance, if we have this closure which increments the counter, it will be typed as something capturing counter. We show that it have a reference to the counter. And similarly, for that closure, it will be typed as capturing both counter and sum. And it also shows that what aliases are in that value. So let's go back to separation check and see one more example. Again, we define two multiple variables, and we have two functions incrementing each of them. And the first function is typed as something capturing A, which is exactly saying that it returns an alias to A. And the second one similarly. And the first example, which parallelizing incrementing A and B, it will type check, because when we want to establish the separation between incrementing A and incrementing B, we follow the aliases by looking at the capture set of the type of these two functions, and we see A and B, and that can be separated. And the second one, similarly, will follow alias of increment A, and we see that then we want to establish the separation between A and itself, which fails. And so we have been talking about distinct multiple variables, but how does that work in our formalism? So first of all, we can assume that two freshly allocated multiple variable is separated because a freshly allocated thing is unaliased with anything else in the system. So that assumption is correct. And how is that expressed in our system? Basically, when we declare a new multiple variable in the formalism, we can freely choose its separation degree, and it can possibly spanning over the existing context. For instance, here in this example, we are defining 3 multiple variables in a row, and the first one, it can have an empty separation degree, and the second one, it can be A, and the third one, it can be A and B. So for each of them, it's everything existing in the context. And although these separation degrees, they are asymmetric, but separation checking, it is symmetric. So the separation between any two of these 3 variables can be established in our system. Okay, so actually, we can view alias tracking from a capability-based perspective. How does that work? So capturing types is original purpose for effect checking, and their perspective is capability-based. So the effects, they are performed via program object capabilities, and capabilities, they are just represented as program variables. So tracking the captured capabilities of a closure is to predict what effect that closure performs. So why does that matter? So actually, accessing a piece of multiple state can be viewed as an effect as well. And we can view a multiple variable as a capability to access itself. So for instance, again, this closure, it is incrementing sum, which is some multiple variable by 1, and it captures sum. It can view that it retains the capability sum, which is a capability to access or mutate the multiple variable itself. And so it's returning alias to sum. And why this perspective matters is that if we view a multiple variable as a full capability to access itself, it is really natural to have a capability derived from this full capability to be just the reader capability, which models the read-only access to a multiple variable. And this is how reader capabilities work in our system. For instance, here we have multiple variable A. We derive a reader capability for it, and the parallelizing 2 reads is OK. But if we want to parallelize reading from A and writing to A in parallel, then that will not work. Okay, so we established some formal results for our calculus. And first of all is type soundness via progress and preservation, and the statement is just standard. And secondly, we formally show that our system can prevent data races by showing that the reduction of a well-typed program is confluent. And the confluence statement is also quite standard, and except that we are using the first gray box shows that it is a store equivalence judgment, and we need that because if 2 programs are executed in different orders, in different ways to like interleaving the parallel evaluations, their stores might have different order of bindings, but these 2 stores should be behaviorally equivalent, and this is what is modeled by this judgment. And also this, the second gray box is just means that for this term and this store, there is some typing context that corresponds to this store, that this term is well typed. So a direct corollary of our theorem is that given to terminating reduction of evaluation configuration, if we get two answers, A1 and A2, then these two answers, they are the same. So the answer of reduction is always unique, although the reduction is, can be interleaved in arbitrary ways and because the parallel let bindings. And in conclusion, we identified, first of all, we identified a dilemma. Well, in data race freedom, so there is a gap. First, on the one side, there is a mainstream type systems, which a lot of code is written, and but they don't care about aliases, and they use aliases a lot. But on the other side, aliases, they are causing data races and other problems. So there are type systems that prevents aliases, but they come with some new principles of aliasing, which require some shift of programming paradigm. So existing codes, they cannot be easily migrated to these new systems. But if they can, they will benefit a lot from the safe concurrency guarantees. So our system is intended to try to fill this gap, and it follows like a control as you need paradigm by default. With empty separation degrees, everything works the same. And once data races are really a concern, we will do alias prevention. And we have studied its formal properties, its type soundness and confluence. And also, we have a prototype implementation which supports separation degree inference that can reduce users' notational burden. And that's all. Thank you.
Okay, any questions?
So first of all, I have a technical question or a clarification. Could you show me slide 17? So there's a binding there, and you're binding A, you're binding value to A in op1, and then I think you said the body is the whole rest of the function.
Yes.
But the rest of the function uses A, so it seems like it's not separated. What am I missing?
Yes, so it uses the result of A, and but data race will happen during the evaluation of A. So the separation that is actually enforced is like all the variables used by the binding term of A and all the variables used by the body of A except A itself. These two parts are separated.
I see.
Yeah. Because
I see. So it's unlike a normal parallel block because you're binding something, and then in the body you're going to have to wait whenever you get to that thing.
Yeah, because when you use A, you will await until the evaluation of A, and that won't.
Got it. Okay, thank you. Yeah, that's helpful. So I have a more design question about, I guess, about the previous slide, but about the whole system. So you have inference, which is really cool in terms of avoiding the need to annotate, but it could also be that I might have a harder time understanding, error messages if there aren't annotations in the code. So I wonder, have you seen this to be an issue? Do you have a particular design approach that avoids the kind of problems that people have with inference for standard ML and other similar languages with inference?
Yeah, so for now we don't have real experience because we haven't tested on real-world code basis. But in those small-scale examples, it works fine. And I think if that is a problem, maybe there are some alternatives. We don't do inference by default, but we have some defaults set for each. We have some defaults for these sort of annotations. And one possible default is that, wait a minute, I want to go back to. Okay, which slide is it? Okay. Wait, it's here, yeah. So one possible default is that when we see the step here, it has to be like separated from all parameters that has been introduced like that, and that might be a possibility. Also, it could also mean that it has to be separated from the body of the function, which is also might be intended by the programmer, but this is quite an ongoing question.
Thanks.
Yeah.
Really cool talk. Cool to see efforts to make this more ergonomic. The thing that I'm curious about is you're comparing to Rust mostly, but then your implementation and it seems like your formalism are more geared towards Scala, which is garbage collected. So Rust, the static semantics prevent not just data races, but also things like use after free, because if you take like exclusive ownership of something, you can destroy it. Do you not have to worry about this because Scala doesn't have a garbage collector, or does have a garbage collector, or do you actually also prevent use after free and similar issues?
So we are not trying to argue that we will replace Rust, but we just want the goal of our the objective of our work is just data race freedom. So we won't care too much about those memory management things, and for that part, Rust is really more expressive and powerful than us.
So just to clarify, that means that you, unlike the previous talk, you don't actually prevent undefined behavior. You only prevent data races.
Yeah, only data races.
Okay, thanks.
Any other questions?
If there are no more questions, then I can teach them. Let's hope this one doesn't need to update.
Yes. Okay. Great. Yes. All right.
So the next talk is from Konrad Zimmermann on Latte, lightweight alias tracking for Java.
All right. Hi, I'm Konrad Zimmermann. I'm a student at Brown University, and this is work done with the four of us here. And yeah, today I'm going to talk about a system that we're calling Latte, lightweight alias tracking for Java. And I should say, disclaimer, this is work in progress. I will talk about some of the things as if we had a tool. We do not, in fact, have a tool yet. We have a formalism that we think translates to a tool quite nicely. And yes. So a little bit of motivation here. Why do we want alias tracking? You probably are already convinced that we care about aliasing if you're here. But as a simple example, and sort of to introduce you to the setting that we're concerned with here, we're trying to do lightweight verification, specifically of Java code. And you may have heard of liquid types, made popular by Liquid Haskell. And this is some work that Katerina has done on bringing liquid types to Java. And in Java, we have a lot of mutation. A lot of the talks have talked about code that can mutate objects, and ours is no different. So here we're trying to verify some account transaction system, and so we want to say that the balance that you have to have at least as much money in your account as you want to withdraw. And here we're trying to withdraw from two accounts the same amount simultaneously. And if you're thinking about aliasing, you might already see the problem here. We can't verify this code. Because what happens if A1 and A2 are the same account? You're withdrawing twice from the same account. And this sort of conflicts with what we want to do with liquid types. We want to have a simple way of reasoning about objects in Java where we can just sort of add. Liquid types are supposed to be like just more powerful regular types, right? We want to talk about objects and be able to refine those types to include things about like the value in the object. And here we have to start thinking about other things. And this is sort of by the nature of mutation and how Java handles objects and all of that, yes, but we want to find a way to actually verify this code easily. And so some goals here that we have as we set out, like I mentioned in the setting of verification and specifically of Java code. First of all, we want sound reasoning. We want to be able to guarantee certain properties about our program. We want few annotations, so we don't want to clutter our code with extra annotations. And also, those annotations and everything that you need to think about should be simple, including the invariants that you have to maintain throughout your program code. Another thing that we want is precise alias tracking, and this is something that will become sort of obvious hopefully as we go along about why exactly we want precise tracking. But intuitively, you can already understand maybe that if we're trying to do a verification versus the data race prevention that we've heard about a lot today, verification requires exact tracking of mutation, or some way to reason about separation, whatever, to track those aliases to be able to guarantee that a certain mutation won't affect another, or another value. And in our system, this is a very important goal that we want to have. We want to have simplicity, and in fact, we value simplicity before expressiveness. So this sort of goes back to the liquid types setting. Liquid types are not meant to be the be-all, end-all of verification. For that, there's other tools, many other tools, in fact. Liquid types are meant to just start down the path of verification, and in our setting, we are okay with trading some expressiveness, which, what does that look like and everything, we'll get into, and we can discuss that further. And this is also sort of to align with how Java developers think and reason about their programs. We don't want to introduce completely new paradigms and stuff, which goes into our constraints that we're trying to accommodate. The first one is accommodating existing code. We want you to be able to start using liquid types in Java without rewriting your program from the ground up using some other pattern. And we want to produce aliasing information for liquid Java, for other tools, whatever you want. We are focused on the verification setting. There may be other applications of this. So some related work that you are probably somewhat familiar with, at least. Separation logic. This is sort of like the standard approach for verification. Just define some logical constraints, specify your separation, reason about how separate value, like non-interference, et cetera, for mutation. This is imprecise, though. As I was saying before, you have a group of things that are separate from other things. We can't give nice error messages. Often in separation logic verifiers, debugging a failure of the verifier to prove some specification is quite complicated. And even the notation is quite complicated. As an example, here's an example from the CN language, which is verifying C code with refinement types. And this is a bit different syntax maybe than traditional separation logic, but it does translate to separation logic. And this is a specification of a binary tree. And another big point of this is that we're defining our predicate separately from the class definition that you might have in Java. And for different properties, you'll need different predicates, each with their own separation properties. This gets complex pretty fast. Another related work is ownership types. Again, this is somewhat imprecise. A nice thing about this is that you got to specify the heap structure and some of your invariants on the objects along with the data structure. So that's nice, but this can get somewhat complex. You have to reason about a different ownership graph instead of just the regular reference graph that the developers are normally used to working with. As an example, this has been done for Java, and here's what it might look like. This is extending the map class. There's all sorts of things that you can do as far as inference here and stuff like that that I won't get into. And it's very interesting work. The question mark here is not gradual typing, but it's more like inference, but anyway. Another related work that's come up in pretty much all the talks is Rust. Rust has an ownership system with borrowing, uses immutable values by default. This has been used by verifiers, so we can do it. But it uses vastly different patterns than are commonly used in Java programs. The borrow checker is often very difficult to understand. This is something that you probably know either from using it or from talking to Rust developers, but there's been papers and research on that. And it requires additional semantics, changes to the way we run code in order to encapsulate some of the patterns that we use in Java. So another work is alias burying. I'll try to get through this list here since you've probably seen some of these, but the idea here is that if we don't use an alias, it doesn't matter, and so we can just sort of go through our program and reason about it that way. This does, though, break encapsulation, at least the way it was formulated first of all, where you would have to include the access fields in a method. Java developers are not used to that restriction, having the access fields be in the public API. And yeah, attempts to restore this encapsulation use new patterns like effects. So some more recent work, and we've heard even some today. Milano et al. Defined a new language that uses regions. This one is interesting because it did focus on that lightweight aspect and easy to use. However, this did use new language constructs and things like that we don't have in Java. Holler and Loico made La Casa. This requires object capabilities, etc. But this is another interesting lightweight approach. So today we will see how Latte satisfies our set of goals and constraints. So our approach, the idea here is that we enforce uniqueness of references on the heap. The heap is hard to reason about, and so we're going to talk about unique references there. We allow aliasing among local variables when it can be, excuse me, when it can be precisely determined. I need. Okay, so, yeah. We annotate the unique fields and the parameters to specify the uniqueness properties that we want. And we infer the uniqueness and aliasing of local variables. So we do this in a type environment that you'll see shortly. So what annotations do we have? Well, we have 3 of them. We have shared parameters, or shared fields and parameters. These are just the default, what you use in Java every day. In fact, our tool would probably not even require you to specify this. We have unique fields and parameters, so these are values that are unique. In a sense, if you have a unique value, you own that value in terms of like ownership types. This means that the value is not referenced by another field or a non-alias variable. And we have owned parameters. So the syntax here is flipped from in Rust. So here we have owned parameters. You borrow an argument whenever you pass it to an owned parameter. This is our idea for this is that you want to talk in terms of the method body. So whenever the method executes, the value is owned by some calling context. So here's an example where we check a stack implementation. Here we are storing unique values in the stack, and this would be so that whenever we verify, we can ensure that no changes to those values occur while they're on the stack. We have a more complete example in our paper, but you'll notice the unique annotations here. And here's an example of a push method for that. So this is hard to read on here. Okay. We have an owned this parameter. So in Java, this is a syntax for annotating the receiver of a method. And we have a unique value. So notably, the value here, whenever you call the push method, is consumed. After you call this, you don't have access to the value anymore. But the receiver is borrowed. So to begin by checking this, to show how our system works a bit, we start off with what you might expect from the declaration of the method. And we start by having some variables, r and n. We assign this.root to r, where we introduce the alias. Here you'll notice we allow aliasing on the stack or in the local environment, like I mentioned before, but we precisely track that in our type environment. And these annotations in the environment are inferred. This is because they actually change during the lifetime of a variable. We don't want to declare something and then have it change later. In the next line, we nullify the root value. This is equivalent to a destructive read. Sometimes you can avoid this with using the local aliasing, as we'll see later, but in this case, we do a destructive read. You could also instantiate a new node with a null next pointer or something like that. Now we create a new node, and we pass it the value and the r. Yes, there we go. And this consumes those two values because we can't allow aliasing outside the values that are stored in n on the heap because we treat the constructors as opaque and we don't we don't impose any restrictions on the heap structure after the constructor returns. Again, we set this.root to n, and which introduces a new alias that we also precisely track here. And so whenever this finishes, we're left with, from the perspective of the caller, just the unique root value, and no aliases exist. So here are some technical details of how we do this. We remove references to the overwritten environment to an overwritten object in the environment through a process that we call isolation. If an object is alias, we move ownership of that value to some alias that we pick. If there are no aliases, then we can't reference the objects that it contains in any other way. Therefore, we can count those as unique values and transfer ownership to the alias fields, of which there may be multiple. And this allows destructive reads of a parent to disconnect a whole chain of values. So what this might look, this does not have my transitions right, but whatever. Okay, we're showing all four of them at the same time. So if you see in the A block here, we have aliases to root and root.value, and then we nullify this.root, and, okay, yeah. And we are left with the A prime here at the bottom, where we have an alias to r.value. This doesn't actually change the aliasing structure, it just changes how we are tracking that. Before that value, r.value, was also alias with r.value transitively. But this changes how we annotate it. And then in the right, if we disconnect this.root, but we have no aliases of root, we can assume that the unique values that it contains are, or aliases of the unique values are unique. All right, so here it is in code. We have, this is a The method of this is using the stack, but now we are trying to deck the value at the tail of the stack, so accessing this as a queue. And we start by creating this alias to n.next.value, and then we disconnect n, and we are left with a unique value. Yeah, there's some other interesting things about this method and how isolation works with it, because the caller of this uses one destructive read to disconnect and be able to traverse the entire tree, but you can see that in the example in our paper. So this verifies fine. We're left with a unique value at the end. One other detail about our tool that is fairly important to consider is that it requires all unique or owned parameters to be separately unique. This term comes from a paper from Holler and Erdersky. And this is actually a limitation of the expressive power of what we can reason about. So it's an important consideration. And the reasoning behind this is that if you were able to reference a unique or borrowed object from two different paths, we're not able to maintain our aliasing invariance and precisely identify the aliases. And because we have this, we have precise alias tracking, and this allows informative error messages even in this case. So our tool can help the user reason about this more complicated requirement. As a simple example here, suppose we had an add method, takes two values, does something with them, and we want to be able to pass it like a value x and a field of x, like here, or an alias of a field, for example, but we can't because we require them to be separately unique. This is also a problem in Rust, if you're familiar with that pattern. Yeah, we think that because we have precise error messages, this is at least something that we can assist the user in reasoning about, but it is a trade-off here. There's no free lunch. Another thing that I mentioned before is how it consumes values. This is sort of like a linear modality. So if you pass a value to a unique parameter, it becomes inaccessible. This also enforces separate uniqueness of unique values. We don't even have to check that. We only have to check that with borrowing, or check it explicitly, I should say, whenever you borrow. Because if it becomes inaccessible, you can't access it later. And here's a simple example of why you might want to consume a value. For this example, it's message passing. Suppose you had some actor that's running on maybe a different thread. You want to send it a message. You send it a message, and you try to then modify the message afterwards. It errors because it's not accessible. And these simple annotations allow you to enforce this invariant. So you could do, for example, copy-free message passing here. Merging is another important aspect of this work. The environments of conditional branches, the delta that you were seeing in the other slides, are conservatively merged here, and this enables us to maintain precision of our alias tracking. And the way we do this is by isolating, using the previous isolation technique that I described earlier, to take care of any values that go out of scope after you exit the branch. And we try to find a common annotation for all the remaining variables. But if we can't, again, it's conservative, we just mark it as inaccessible because we can't figure out what the aliasing is. This is, again, a limitation on the expressive power, but here again, we can assign precise blame whenever this fails. And by fail, I mean like it just marks it as inaccessible. As an example here, we might have a method that tries to do something like this. So in one branch, we instantiate a new node, and in another branch, we try to use the root node. But if we try to do this, we can't, because we have a unique value in the one branch and an alias in the other branch. there is no way to unify those annotations, and it results in it being inaccessible. But here again, we can precisely point, say, in this branch, it's this way, in this other branch, it's this way. Do something about it, I guess. And here we could, for example, do a destructive read, which fixes the problem because, yes, that's a problem I fixed in a later copy that apparently I did not copy here. But anyway, it's fixed because it's now unique in the other branch. Oh, wow. Okay, yeah. So our goals, recapping them. Sound reasoning. We think that this is sound. We were really excited about it at first because we were like, it's so simple. And then there's like edge cases. Wow, who would have thought? So, yeah, but we think it's sound now. We have yet to prove this. But we do have a formalism, and to our knowledge, it is sound. There are very few annotations. This is pretty easy. There's 3 of them. In fact, just 2 for fields. 1 is default. You don't even have to specify it. And local variable annotations are completely inferred. Again, this is because they can change during the lifetime. And we could use like tools and whatever to show this, which I'll get into later. But yeah, we do enforce simple invariants. At least we think it's simple to reason about. You have to reason about uniqueness on the heap. There's no separate graph of ownership or anything to reason about. We precisely track aliasing, as I was talking about earlier. And by precision, I mean we specifically identify an actual path that aliases this value, or that also references this value. And anything that we can't precisely track, we just say you can't access it. It's not allowed. As I was saying before, this lets us do interesting things like precise blame whenever this fails, things like that, to help the user reason about some of the more complicated aspects. And I hope it's pretty clear that this definitely favors simplicity over expressiveness. Where we draw the line is up for debate here, but yeah. We do want to further evaluate this and see how expressive it is. We have some examples that from where we compared it to other work, and it seems relatively expressive for some definition, but we haven't evaluated it. So yeah. So yay, we did it. All right, we're all done. Except, well, there's a lot of questions about this. Is uniqueness alone expressive enough? That's a question. Maybe we can specify some unique core of objects and then use our liquid Java reasoning, like type state and et cetera, to reason about the structure of other values. But this is a question. Also, the usability, is this easier to understand than other approaches? We have yet to evaluate that. Should we allow temporarily breaking some of these invariants as long as we can show that they're restored? That's another question. It remains to be done to actually integrate this into tools, and we've done a lot of discussion on what the best way for this is. Do we want to encode the annotations in a separation logic and then pass that off to something else, or what should we do there? And developing IDE integrations. This is, I think, some interesting stuff here that is possible because we have this very precise alias tracking. We can highlight aliases, would be one example. We can do diagrams of the heap structure. We could precisely identify the source of some other errors that occur during verification, et cetera. So yeah, that is Latte. I'm Conrad again, and yes.
Okay.
I guess a little bit of shameless self-promotion. I am currently an undergrad going to grad school soon, so if you have any opportunities, I would be happy to talk to you.
Okay, so do we have questions?
Yeah, thank you very much. It's very interesting research. I was wondering, would you consider adding immutability as an additional parameter in your system? Because you could easily get around the issue of uniqueness, of separate uniqueness, by just making the system believe that objects are immutable as long as they are unique, as long as they're immutable.
Yeah. So that is one thing that we did discuss. We thought about it a little bit. It turns out that it's like slightly more complicated to reason about than what you would initially want it to be. I'm forgetting exactly why right now, but yes, that is interesting. An interesting option that we should explore more, I think. Yeah.
If no one else, I have. Okay.
So you mentioned sound reasoning. What exactly do you mean? So data race freedom?
So, yes, I should have specified that. By sound, what I mean is that we actually do precise alias tracking. So if you modify an object, it should only affect the things that are aliased that we know are aliased and annotated as such. There's certain things, in our formalism we have like a way judgments determining like the whole set of things that are aliased with an object, that sort of thing. So that's really what we're getting at, is that our aliasing is correct, or our aliasing analysis is correct, yeah.
And if I can add just one word to that, going back to one of Conrad's first slides, we intend for a client analysis of this to be liquid types for Java. Mm-hmm. So a verifier, of course, needs to know what the effects of an assignment are. And so it has to eventually be sound for that purpose.
Hey, this is really cool work. Have you worked out the interactions with Java's generic types yet? Does it stay simple? Well, I didn't see any examples with generic types, so that's why I'm asking.
Yeah, that's a good question. I think our current hypothesis is that yes, it stays simple. There is some questions about, do you want to allow polymorphism in the annotations? That would be something that we would need to work out. We do have subtyping. It seems to work as you would expect it to. Yeah, so I expect generics to work similarly, but yes, that's also remains to be like done and shown that actually works.
Doc, I was wondering, you may have said this, but I may have missed it. If you have a method that takes a owned parameter, do you have to ensure that that doesn't escape from that method, so it gets returned to the caller? Yes. Or can I take a reference and return it, I guess is the question.
Right, it cannot escape from that method. It has to stay local, yeah.
So maybe that's one question to ask in your open questions in expressivity. That seems like a fairly common pattern, being able to get reference to the contents of something that you call via a method call, which is what then, for example, Rust is lifetime tracking for. But yeah, thanks.
Yeah.
So with the topologies, we're only allowing unique pointers, you're going to be quite restricted in what you can do. So like your example where you had a queue, you looked like it was an O of n operation to do a DQ, whereas I would prefer it to be O of 1 and have 2 pointers to the tail. So do you have any thoughts on how you could be slightly more liberal in the uniqueness?
Yeah, so this is the really kind of maybe the big question that remains. I'm not sure. I mean, so the easy answer here is that we let things be shared, and then you can do whatever you want. And our hopes is that we can integrate that into Liquid Java in a way that nicely interacts with our uniqueness system, where we can specify more complex structures in the liquid types logic and save the overall heap structure, like the global invariance that we want in our uniqueness system, but that remains to be seen. Wait, could you clarify what you were saying about the stack?
So you had a DQ operation, but you traversed the entire stack to do the DQ, whereas if I were implementing a queue, I would have linear pointers effectively, but the last thing gets 2 pointers going to it because
Yes,
you have a tail
right.
pointer.
Right. That is one thing that, yes, we need to, that's, yeah, it's unclear how you would do that in the current system. And so I would hope that we could encode, we could have the tools to do that in the, on the liquid Java side to say that this is, you know, we have a last value. But yeah. All right.
Seems that people were quite interested in this, so hopefully that will be a good omen for your graduate studies. Seems so to me. So we can then thank Konrad again. Thank you. Okay, and that's that. So now it's time for the lunch break and then the talks afterwards. So one small thing, if you are speaking and you didn't speak before, then could you come 15 minutes before the session so we can figure out the setup? Thank you.
Is it?
Why isn't it direction?
Wait.
It's okay.
Yeah, it's not there. Okay. The fastest way might be I just. I don't know, maybe Mac OS does some weird things.
It's over there. How fascinating.
All right, so it seems like we're actually ready to start. So thank you again for coming to the third session. Thank you. Well, I'm supposed to be somewhere on TV. Do I really want to be recorded, or do you just want the deep DJ voice? You want the deep DJ voice? Thank you. Thank you for coming to Owako again after lunch. We're all fall asleep, but luckily we have Inshinju here to talk about a paper on the mechanized theory of box calculus. You'll have heard an awful lot about the box calculus this morning, I know, with Martin's talk and everything. So. Yeah, so anyway, good to kick off again. And as I've already said, we'll have 3 talks in this session, then a break. And just before we go to the break, I will see what people would like to do this afternoon. Effectively, you can start thinking about this. We do have the room for a 4th session if we want it. Previous IWACOs have had some level of discussion about what people are doing, perhaps if people hadn't had a chance to present, or if questions have emerged that it might be useful to talk about. Or alternatively, we can go to sleep or go to the pub. Anyway, Yushen.
Okay, cool, thank you. So today I'm Yichen Xu, and I'm going to talk about the mechanization of the capture calculus you just saw in the morning, and we call it box calculus. There are some historical reasons, and we'll explain it. So I'm Yichen Xu, and this mechanization is done by the first order Joseph, and I'm going to present on behalf of him because he cannot make it today. Okay, wait. Okay. I think it died. Okay. Okay. Is it okay? I cannot see my cursor anymore.
You can disconnect the cable and then try it.
Like that. Okay, and
Still stuck.
it's still not working, I think. Okay. It's not responding. Yeah. Okay.
I don't know how it works.
Not sure what's going on. I cannot see the cursor. Okay, it's back.
Okay, and where was it? Do you know?
It's
on the flash drive?
But I think I can copy it out so that it can be more seamless.
Just from
Okay.
Yes, Finder. Thank you.
Okay, and there's a USB drive, and maybe let's copy it.
Which one is it? This one?
The first one, the mechanized theory.
Then we need to move it.
Over there.
But
Yeah,
yes.
It's working. It's working.
This way.
Yes. Okay.
And then.
There's view, and I think this command might work. Does that work? Okay. No. Okay.
Yes, it did.
Okay. Nice. Thank you so much. Okay. Sorry, we wasted 5 minutes, but I can speak faster. Yep, so this is basically a mechanization of capture calculus. And what is it? So we've talked about it in the morning, but basically it is experimental new statistical analysis implemented in the Scala compiler that supports a lot of things like checked exceptions and memory region management, and also like things like algebraic effects. So, and capture calculus, it is the theoretical foundation of capture checking. And so its basically idea is that it will check abilities in types, and it is capable of ensuring the scope of scoped abilities. No. Okay, it's not dying. Okay, so to investigate capture checking, we actually have quite some attempts, and the post calculus or capture calculus is now the final outcome. And previously we have system CF sub, and we already have a mechanized proof of system CF sub. And there is a main difference between CC and CF sub, which is CC is now in monadic normal form. And so previously, we have migrated the proof of CF sub to use monadic normal form too. And this project, it further migrated that proof to mechanize CC. Okay, so this is a nice diagram of the development of these mechanizations. And okay, we'll first talk about what is those capture calculi. And the first version, CF sub, maybe not the first, but one version which is on which our mechanization is based on is CF sub, and it looks very much like CC. And for the main difference from it to between it and the system F sub is that now types, they have an additional qualifier called capture sets. And the capture set, it can either be the root capability or a set of captured variables. And for other constructs, it looks very much the same as in system F sub. And there's one problem of it. So in the end, we find out that to do its soundness, we have this polarized, well-formed judgment. And this is really complicated. And another challenge of system CF sub is that it has a limited expressiveness power in terms of generics. For instance, let's see this example. Sorry. The cell type is just a church encoding of a container of one single element. And if we want to write a function which maps the cell, we apply a function on the element inside the cell, we can possibly write it this way, and but it is really straightforward. But the problem is that we have to decide the capture set of the result type. And what is it? Hopefully, it should be it should be the capture set of B. But we don't know what it really is. So in the formalism, the best we can write is just a star, which is the top in the capture set hierarchy. So that is really imprecise. But if we can force the generics to force the type variables to be pure, and without any capture set, for instance, here we can assume that B yet is a pure thing, then actually we can make it more expressive. And to do that, we have a new device called boxes. And box a type, we can encapsulate what is captured in this capturing type into a pure type. And later on, we unbox it. And for those generic functions, we just assume that the type variables, they are pure. And that will give us a precise signature of such functions. And we can use the box mechanisms to properly reason about what is actually captured under the hood. And yes, that's why we introduced system system CC. And so first of all, it is in monadic normal form. And secondly, we add the box and unbox mechanisms into CC. And so the main difference we enforced is that for type variables, they must have a pure upper bound and a pure instantiation. So we don't have to think about, well, which capture set you put on these type variables. It's just pure, and all the captures are hidden in the boxes. Okay, so previously we have the distinction between pre-types and types. So for pre-types, it's just the types without a capture set. And for types in CF sub, it is a type qualified with a capture set. But in CC, we don't really still maintain this distinction. It's still stratified, but we can implicitly make a shape type or a type without a capture set to a capturing type by putting an empty capture set on it. So, and also, we have this new formulation, and the key difference is that the type variable previously is considered as a capturing type. It can have a capture set under the hood, but here it is considered as a pure type. Okay, I think there's a mistake. Yeah, no mistake. So here it is considered as a pure type without any capturing. And the full expressiveness is, of course, recovered by the box and unbox mechanisms, because we can now make a capturing type into a pure type and then later reveal the hidden capture sets inside the box. And now, with this formalization, we have much simpler well-formed judgment. So it's just standard. The only thing is that the capture set, it can only mention defined program variables in the context, and other than that, that is the same as the well-formedness judgment in system F sub. And the main typing rule with the box mechanism is just these two ones, and one is the introduction rule for boxes, and another is the elimination rule for boxes. So, and note that we cannot box or unbox when the captured variables, which is C here, isn't in scope. So this is how we ensure scopeness in capture calculus. So then we did the mechanization, and we made one simplification. So previously, because we have the distinction between pre-types and types, and that basically shape type, the ordinary types, and the ordinary types plus a capture set, we have this mutually inductive construct in the old Koch proof for CF sub. But Koch isn't very good at dealing with those mutual inductions, and it might take a long time to find the decreasing order of these inductions and make the proof check really slow. And now what Joseph did, what we did is that we can merge these two types into one. So we put all the type definitions into one inductive type, and we have one additional judgment which checks whether a type is pure or not. And in most of times, we can just state one theorem on this data type instead of state two mutually inductive ones. And when we really need to have a mutually inductive theorem, we will use the pure judgment to differentiate between pure types and capturing types. Okay, so, and also, other than this simplification, because now our well-formed judgment is much simpler, it is a huge simplification in the mechanization too. And there are some possible future work that could make the proof check faster. So basically, our proof is in monadic normal form. Is in locally nameless with a cofinite quantification. So that's kind of a classical setting. And here, in some cases, we will use that pick fresh tactic to find a fresh variable that is not mentioned in the current context. And for that one, the tactic have to gather all the exclusion list, which is names already present in the context, and pick a fresh one. And we have those tactics which will work on this exclusion list to reason about it is distinct from anything else. But here, actually, the list by default will include all the atoms or names in the system, which includes both variables and type variables. So we think that if we can differentiate between variables and the type variables by just parameterizing its type with a tag, then we can get a smaller L in most cases. And because such cases are really common in the locally nameless proof, we think this can further speed up proof check. And so I can conclude my talk. And so CC is the box calculus is basically a huge simplification from CF sub. And with the introduction of the box constructs, it have and monadic normal forms, it have a simpler well-formed judgment, and it can have better expressiveness in terms of generics. And also, previously, the Coq proof of CF sub is 12,000 lines of code, but after we migrating it to CC, it is only 7,000 lines of code, and it is almost halved. So this is a good proof that the new system is kind of better than old one. And finally, the soundness proof is online available on this link. And there is a technical report of our mechanization as this URL too. It's okay. And that's all. Thank you.
It's a pretty quick talk. Does anyone have any questions?
Thank you. It's a huge work. Congratulations. How much can I reuse?
If that depends on what your system look like. If that's somehow similar to capture calculus, like you want to track captured variables or track a set of things in your types, then I think a lot of infrastructures for those related to finite sets and how we deal with these types can be reused. But if your system is quite different, then I don't think it is easily reusable. And yeah, that's it.
Just a clarification. So, for instance, you have a small algebra for for reasoning on the capture, right?
No, we didn't abstract it as an algebra. Yeah.
Because I was going to propose, if that's something separate, can we just put there a different algebra?
That's a good idea.
Any more questions?
Also, it seems that one of the advantages of this is that you wrap up the generics, and then you can wrap up any capture thing in a generic, and then effectively when it's in a box, you can be passed around anywhere. Have you thought about possibilities of constraining that?
Constrain that?
Yeah, I mean, maybe you don't want to be able. I mean, for example, if you wanted to model, I shouldn't say this, a Rust style ownership with generics, there are always constraints about where you need to maintain references or otherwise to objects. And it seems to me if you put an object into a generic container and now you can move that anywhere, you wouldn't be able to maintain the necessary invariance over the Rust heap. This isn't a criticism of your work, but it's not clear how it would be applicable in that case, is what I'm thinking.
Okay. I think currently with the box mechanisms, we do enforce some sort of constraints, which is the scope of the capabilities. So if you box something that captures, say, can throw, so the capability to handle exception, and that box thing escape the scope of the exception handler, then you cannot unbox it and use the value again.
Right,
So
but it still exists.
yeah, it still exists. But you cannot use it, so...
But it still needs to exist. And if you, I'm just really trying to see the limits of the way the system works. It's not a criticism of your work. For something like can throw, that's probably absolutely fine.
Yep.
But if you wanted to use this to do memory allocation, for example, if something escapes in just the same way, it's now escaped.
But if it doesn't, if you cannot use it, then it's fine. It's like having a pointer but not having the right to dereference it. You can have a pointer, it's a useless value.
Well, yeah, you can. Indeed, you can. Unless it gets garbage collected or whatever.
Yeah, sure, but we don't know what using the value means. Like if you're not allowed to use the value in any way, then you just have a useless value floating around your program and you cannot do anything useful with it.
Sure, I know that, until you can unpack it.
But you can't unpack it, as you said. So you would capture your pointer that has a valid that points to valid memory. Then it escapes, so it no longer points to valid memory, but you can't use it. So you can't dereference it. So it's fine. Like nothing bad happens. You just have a big pattern.
Okay, all right, well, thank you anyway.
Hello. Yes. So maybe a more Coq technical question, but so if I understand correctly, this other system, CF sub, has this mutually recursive, mutually inductive definition, and Coq doesn't handle that very nicely. And in the CC sub box, you do this trick where you do a single thing and then you have an inductive thing that says it's well formed if blah 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 blah, and then that simplifies everything. How much of these 7,000 lines is that simplification? Could you play the same trick on CF sub and reduce the size of that as well and the complexity of that as well, or?
I think that's a good point. I'm not sure, but I won't say that this trick is reducing the lines of code that much, because the cases, they are still there, but they are just merged into one theorem. So,
right.
Yeah.
Okay.
Is that so? Let's thank the speaker again.
We are early. I don't know if we want to start at past.
I'm happy just to carry on unless you know you have friends coming that don't want to miss the start of the talk.
That's fine. What am I doing here?
The other reason I think it's good you check is because that way it's like, whoop.
Yeah.
Okay, that's on.
Is it now?
Maybe move the presentation out because it likes when you open it for the USB drive.
I see.
Put it on the desktop.
But I think I launched something.
Yeah, it's on the screen.
See. Just that. No, that's not it. Do you know the shortcut? Do you know the shortcut?
No.
Full screen. L. All right. Yeah, so I'll get started. So I'm Aurel. This has been a joint work with Jonas Hansen, Alexander Summers, and Peter Miller. And I'll be talking about specifying and verifying iterators in Rust. Before I get started, I want to sort of clarify the scope. This is about iterators in Rust, which are many things, but are not, for example, iterators in C++. In C++, you have similar concepts called ranges and views recently, or in Java, you have these streams. So that's the kind of feature that I'm talking about. So to begin with, I want to make this kind of point that iterators in Rust hide a lot of complexity, which is both good because your code looks nice, it's quite maintainable, it's easy to read, but of course there's a kind of cost to this, right? The compiler has to do something about this, and also to specify and verify these things, we'll find some challenges there. So as a very, very quick intro to iterators, let's construct an iterator chain. So here we start with a vector of, let's say, integers. We call this iter method to get an iterator. We call map. So here we will apply this operation of adding 1 to each element in the stream. Just note this is the syntax for closures in Rust. And to make it more interesting, we'll also make the closure have a side effect. So in this case, the closure will mutably capture this sum variable and update it so we have a sort of cumulative sum of all the elements this map has seen thus far. And so the result of map is yet another type that implements iterator, so we can apply more operations such as filtering out only the even numbers. And finally, filter gives us yet another iterator, so we can collect this into, say, a vector. So this is what we call an iterator chain. It's simple, but if you look under the hood, the compiler has to think about a lot of things. So if you spell out the actual full types that are going on here, they get kind of gnarly because sort of everything has to be tracked really precisely by the Rust compiler. So looking concretely at this filter type, we see that the final type of this filter iterator contains in it as a type parameter the map iterator, which contains in it the iterator over slices that we got to. This is good because it allows the compiler to not have to box values, which in Java streams you have this int stream type to avoid this kind of thing. It means that the compiler, because it also keeps track of precisely which closure type was actually passed, can generate code which is as optimal as if you wrote this loop yourself. And of course, in Rust specifically, the closures, especially the first one, captured some variables, so we need to keep track of lifetimes. But then let's look at what we can do when actually verifying this code and what some of the challenges might be. So the first very general one is how to even specify iterator behavior at all. And then as sort of sub-problems, I'll focus on how to specify iterators which are parametric in a closure, and also ones which are parametric in a previous iterator in a chain. So this is all done in the deductive verifier called Prusty that we work on. It is a deductive verifier, which means when you verify some code, you get pretty strong guarantees about what just happens. And the cost there is that you are expected to provide some specifications. So namely, we provide, as users of Prusty, preconditions and postconditions on methods and things like loop invariants. Another thing that Prusty is, it is a modular verifier, and I mean method modular and sort of type modular. So we would like to express the specifications once and for all. We want to have the specification for the iterator trait and for iterator implementations. It shouldn't be the case that for every single iterator chain that we build, we need a completely new specification. So let's start with this first problem of just specifying iterator behavior at all. So here we have a counter, which I'm not showing the implementation of the iterator trait, but you can see its behavior very simply. It has one number which keeps incrementing and one upper limit. And so as we repeatedly call this next method, we get the values 1, 2, 3, and then it tells us, okay, I'm done. And this next method is the one crucial part of an iterator implementation. It's the one required method. So how do we specify this? So our answer to this is to provide these specification ingredients, and I'll explain each of them now in turn. So here we can see sort of the state flow of this iterator, as we call this next method. And so the things that we focus on are, firstly, when does the iteration actually stop, if ever? So for this, we define some kind of stopping condition. And here we choose to define it as the function from the state of the counter, which tells us whether it should stop. And in this case, the condition is whether the numbers are equal. So then, ignoring this part, when it's an iterator, what it matters to us is, of course, the sequence of values it actually produces. So we talk about this as this produced sequence of values. And note this is sequence as in something that is only available to the verifier and not an actual collection type. And also focusing at the states themselves, ignoring the fact that we're actually calling this next method. Each step in this iteration, we can find some kind of relationship between successive states. So we define this one-step predicate called step, which relates a previous state to a current state. And we can see that with each step, we increment the first number by 1, and crucially, that the second number stays the same. But there's also one more situation which we need to account for. And so, for example, if we have this kind of mutate method which accepts an iterator and it accepts it by a mutable reference, well, we don't know what the mutate method might do. And in particular, it might call the next method of the iterator some number of times. It might be 0, it might be more. In this case, we just don't have any specifications for mutate, so what can we actually assume? And so for this, we want some kind of predicate which we call leads to, or an n-step predicate that still holds after arbitrarily many calls to the next method. And so in this case, what we can find is that no matter what the value of the counter is after the call, it must have monotonically increased. It cannot have decreased. And the limit itself is also not changing. So cool. We have defined these ingredients for our basic counter iterator. More generally, they will have this kind of signature for just iterators. So this was our first problem, and our solution to this was to define these 4 specification functions. So then let's get to a more complex case, which is the closure parameter case. So here I will define yet another iterator, call it repeat, which is generic in this F type, and it says this iterator contains a closure which will give out some values and accepts no parameters. As an example, we'll construct essentially the same thing as before, a counter, just this time it does no stopping condition, and its behavior is like before. So the question here is, well, how can we define these ingredients, these predicates and the stopping condition when what we're talking about is a closure contained within this repeat iterator? And in particular, in the example I showed, it seems like this is the sort of flow of states that we have. That we have this repeat iterator which somehow calls the method, and on the side there's this variable x which keeps increasing, but it's hard to find the connection. But of course, this is where we realize we are actually in Rust. And so there are some guarantees that Rust ownership gives us. So namely, repeat owns this closure for the duration of its lifetime, and in turn, the closure owns or mutably borrows or captures, whatever you want to say, this X variable. And so actually the way we can represent these states is maybe more accurately represented this way, where the repeat iterator contains this X variable for the duration of its iteration. And so more generally, this repeat iterator will contain some function states. So now the question is how to specify the repeat iterator. And so here we will turn to some of our previous work in closure verification. So there is also a similar concept for sort of a one-step predicate of a closure. We express this in specifications with a call description. So this is the general syntax, and essentially this is an assertion which states that a call has happened, that a call to this specific method happened with some parameters, which in this case there were none, taking the closure state from one state to another, and optionally, not in this case, maybe there was some result. This is vastly simplified, but this is sufficient for this talk. So this is a useful assertion, and it just talks about calls to functions. So in the case of the repeat iterator, we can pretty directly use it as, or reuse it as the one-step predicate of the iterator. We're saying that the one step of the repeat iterator is the call description of this method f. And similarly, if we pass the repeat iterator to this mutate method, well, we also want some similar notion of an n-step predicate for closures, which we call a history invariant, which you can also define for the closure. So cool. We have used our closure specifications to define the behavior of a repeat iterator. And now the question might be, did we actually specify anything at all? Because it seems rather abstract. So here I want to bring up again the point that Prousty is meant to be a modular verifier. So in particular, we only want one specification for this type. And so although at the point where we specified repeat, we defined this rather abstract call description to be its step predicate, what this actually allows us to do is that at a particular call site where we know the definition of the closure, where we know its specification and history invariant, we can instantiate the specification, and basically the step predicate of repeat becomes this one, where we can talk about the X variable actually being updated. And what is important is that this step should be done by the tool, or in other words, our specifications should allow the tool to perform this instantiation automatically rather than have the user write new specifications for each iterator chain. Yeah, so just to summarize, for this part of the problem, we used call descriptions and history invariants. So moving on to yet another slightly more complicated situation, we have the slightly simplified version of the map iterator from the standard library. So this is now what's called in Rust terminology an iterator adapter, in that it takes an existing iterator, the previous iterator in the chain, and then adapts its results to become, yet again, an iterator. So reusing the repeat iterator as the previous link in the chain, we can construct map manually by just passing the iterator as a parameter and now applying this double enclosure, for example. The behavior is unsurprising. We can once again think of the state of map as being composed of what it actually contains, which is the state of the iterator that's previous in the chain and the state of the closure that it's being used with. So now let's focus on one application of this next method. So what the map implementation will actually do is it will query the previous iterator in the chain. So it will call the next method. And here we assume that it gives us some results still, so we'll call it some v. And this v value will then be used to call the closure contained in the map. So this is this call mute. So to define the step predicate for map, For the time being, we will existentially quantify over this V. I'll talk about this in a second. We'll say that V itself was passed to this call mute representing the function call, taking the, in this case, F0 states to F1, and that some V value itself came from a call to iterator next of this I0 state moving to the state I1. So this is a kind of generalization of the call descriptions that we had previously, in that it's not only describing closure calls, it's describing arbitrary method calls with slightly more interesting things we can do about the pre-state and post-state. Yeah. What we're not showing is that, of course, the previous iterator can return none. This is just some kind of match that we need in the predicate. And that in the actual implementation, we also avoid this existential quantification with something called ghost sequences, just for better automation. More details in the paper. So our problem in the third case was how to specify iterators with iterator parameters, and for this we generalized this previous concept of call descriptions to talk about more general APIs. And as a final point, I want to bring up something which I title incremental verification, I guess. If you imagine applying this methodology to a large code base, you might face some issues if this is implemented sort of naively. So in particular with SPLASH'23, we believe that it's important that you can sort of gradually buy into verification and stronger guarantees by sort of gradually providing stronger specifications, for example. And if we just made these iterator methodology ingredients part of the iterator trait, well, this would be a bit of a problem, because you can implement your own iterators, and now suddenly your code base doesn't verify because you don't have definitions for these ingredients. And so the problem is basically how to add the specifications to the iterator trait without forcing the code base to replace all usages of iterator with our own trait or something like this. So first of all, there is one problem here that's already solved, which is that there is a type defined in a different crate, in this case the standard library, and it has some methods, and we want to attach specifications to them. This is simply called an extern spec. So what we could do in SPLASH'23 is define an extern spec for an iterator, add some preconditions and some postconditions. Yeah. But if we actually start to try to use this methodology, well, the problem is obvious. Like, I start writing one of these postconditions that say the iterator will not return none unless it has finished its iteration. But I cannot call done because this is not a method of iterator. So how do we actually load our functions into here? So the solution we go for is we define all these methods in a different trait, make it a subtrait of iterator, so anything that it implements this iterator spec must also implement iterator. And then we use our novel concept of type-dependent contracts. So this is a contract which only applies if an additional trait bound is satisfied. So namely, if the current implementation of iterator also implements iterator spec, then this is the contract. And you get sort of a stronger contract that must be a behavioral subtype of it. And then to actually provide specifications for all these standard library iterators, these turn into concrete implementations of iterator spec of our own specification extension trait. Yeah, and so just to re-summarize, I guess, our problem was how to integrate with realistic code bases. We applied this type-dependent contracts idea. We have found, since working on iterators, that this idea is rather useful in other situations. In particular, there are many marker traits in the Rust standard library where this kind of thing naturally fits. And the particular design we chose, where the trait bound that it needs to be satisfied is written in the extern spec of the trait being extended also fits in very nicely with the idea of trait coherence in Rust, where essentially this is a system which ensures that for any trait method call, there's only ever one definition. So we want a very similar property, which is that for any trait method call, there is only ever one contract. I will briefly discuss some related work. There was an old challenge in 2006 about specifying iterators. One of the solutions was this reasoning about iterators with separation logic, which was a rather manual approach. In 2018, there was a much nicer, or more automated rather, approach, which has sort of similar ingredients to what I described, but it's not general enough to describe, for example, composition of iterators or to talk about the state of the iterator as it evolves. And finally, very recently, there was a talk you might have seen by Xavier where where Rust iterators are also specified and verified in the Crusoe system. This was work developed in parallel with this, just to be clear, but they do not address this code-based integration problem. Some future directions, I suppose. This idea of these type-dependent contracts is very similar to what trait specialization might do in Rust eventually, when it's sort of more publicly available and more stabilized. So it could be that type-dependent contracts can be eventually replaced with this proper feature. You might have noticed that this n-step predicate leads to feels very similar to a type invariant for an iterator, and indeed it is. We designed this methodology for verifiers which do not necessarily have such a feature. And finally, itermute, which is an iterator which allows you to mutate, for example, the elements of a vector as you iterate it, is something that we believe our methodology should support, but the Prusty underlying tool doesn't at the moment, so oh well. And yeah, this is it. Thank you.
Great. Thanks for an interesting talk. And once again, are there any questions? Yes.
Hi. Thanks for an interesting talk. At one point you said, so here's the existential quantifier, and I'll get back to that. So I'm a bit confused about you're writing steps 2 as a Rust function, but you're using it in the specification. So should I understand that as like a pure thing, which is not actually Rust code that will be run, but it's just to help verification? And then the second question is, how do you do this with this existential quantifier? How does that?
Yeah, so all the ingredients of the methodology that I presented in the iterator spec trait are marked pure in Prusty, which means they should be side effect free, deterministic, the usual stuff. But they're still Rust code. Like you could run them, but they're also suitable for use in specifications. For the existential quantifier, so the solution we have is basically called ghost sequences. It maintains for something like map, you maintain a sequence of all the states of the closures and the previous iterator. And so the value that you actually obtain from the call to next of the previous iterator is determined from this existing state. At a concrete instantiation, at a concrete call site, these sequences sort of become spelled out, if you want, and allow the verifier to do this kind of reasoning without actually having to prove existential witnesses.
Is this n times steps to method just always the reflexive transitive closure of the one-step thing, or are there useful instances where it's more general?
Yeah, we describe it as the transitive closure. I think it's generally what you want. in general, we ask the user to actually provide this because it's the same problem as inferring an invariant of a loop. So, I mean, you can have a less specific, less precise invariant, of course, and maybe that's sufficient for some proofs that you do.
All right, thank you. Thanks for the talk. Okay, then let's thank the speaker again. I think it's best if you put it on the desktop so that it doesn't like read the flash drive for your presentation. Yeah.
Wait, okay. Oh, fudge, okay. Ah, yes. Okay.
I guess the underlying foundations of formulas in the first talk, and this one, the practical issues of actually, doing it all. This one is, well, it's about a debugger.
Yep. Okay. So, hello, I am Peter Sean, a second-year undergrad at Harvard College, and today I'll be presenting my work on XIII, which is a step debugger for static semantics. This was under Dr. Dimi Verkordon of Northeastern University at the time, and Professor Nada Amin of Harvard University. So what is XIII at a high level? It's a step debugger. And instead of allowing you to step through the dynamic semantics of a programming language, it allows you to step through the static semantics of a language that has ownership and aliasing. So it's basically a step debugger for a Rust-like language. And because Rust is the most famous representative of languages with ownership and aliasing, I'll be using Rust as like a notational abuse for Rust-like languages throughout the remainder of this talk. And Rust was our inspiration for starting this project that is XIII. So to understand what XIII is, it helps to understand what it is meant to be. So I'll motivate XIII, and I'll do this in two parts. So the first one will be why pedagogical tools for Rust are necessary, and the second is why XIII specifically. So the first, memory safety is hard. According to, I think, MITRE, 70% of security vulnerabilities are due to memory safety issues. And there are programming languages that offer memory safety through garbage collectors like Java. But memory safety and efficiency, that's the hard part. While thankfully Rust offers a way to marry memory safety and efficiency together, it does it through a novel type system that has been demonstrated to be hard to learn how to use. So I'm going to split people into two sets. First one would be programmers with systems backgrounds and those without this type of background. For those with background in systems, it's been demonstrated that they have a hard time just like figuring out how to use a compiler that thinks about stuff that they typically think should be dynamic behavior. They find it hard to reason at a compile time. And as discussed in previous talks, for folks with this background, they're used to using a lot of patterns that Rust just completely disallows. And for programmers without this background, a lot of the borrow checking rules are just unmotivated. They're also unsure why we even have these, what they even are. Now, at the end of the day, like teaching these rules isn't that bad because there's only like a few rules about, oh, piece of data can only have one owner, piece of data can only be mutably referenced by one thing, or maybe you'll have multiple immutable references. There's also a lifetime rule where it's like, oh, reference cannot outlive the owner of the data it refers to. And these rules are easy to teach, but unfortunately knowing these rules doesn't suffice because we have a harder problem that's called incompleteness. And we can't solve incompleteness no matter how much we try to do. And it's just hard for everybody because even if we know these rules, there are cases when we're coding in Rust where we have perfectly valid memory safe code, but the Rust compiler just doesn't recognize that it is safe. An example of this would be with like splitting borrows. So now why Oxidize specifically? So let's look at the existing pedagogical tools that exist for Rust, and I'll contrast this with Oxidize. So the first one is Rustlings. Rustlings is a fantastic tutorial on how to learn Rust, but it teaches only the rules and doesn't teach how the borrow checker actually works. The Rust compiler error messages are famous for being fantastic, but they're too good at times, and it has been shown that programmers were tempted to just blindly copy the compiler hints and their suggested solutions. And because the temptation is that great, we just often end up doing so. So it's not going to teach them how to actually use the language very effectively. And occasionally, the Rust compiler hints are wrong. There's also the pedagogical tool that is RustViz. And what RustViz does, it allows teachers to manually annotate a snippet of Rust code. And it will generate visualizations on the memory events. For example, like when something is being moved to another location. And they specifically require manual annotation because what they want to do is they want to allow the teacher to highlight the relevant and most important memory events. And that is good, but I'll cover like in contrast why Oxidize is like different from all of these. So first, we teach actual borrow checking. We don't teach the rules. It's like how the borrow checker actually works by simulating it through a static step debugger. We try to force the user to think because we don't have like these fantastic error messages, and we show the user how everything is going, so they're kind of forced to confront the material. And there's no expert necessary, so you just write up some code, you run a step debugger, and that's it. There's no manual annotation necessary. So I'm going to do like a quick demonstration. This is not a live demo, but this is just like on the slides. So we have this snippet of code, and as we're stepping through it, we'll see that there's 3 types of context. So there's the type context, there's a memory map, and there's some borrow layout. So as we step through this code, we see that the contexts get updated. The borrow layout will check out, will just like do everything that borrow checker actually does. Memory map is maps variable names to memory locations, which are natural numbers. And the type context, it stores the mutability of the variable and the type of the variable itself. Note that because it's a static semantics step debugger, it doesn't actually care about the values like 3 and 5, it just cares that these are ints. And eventually we're going to get some borrow checking error. The issue here is that we can't assign to an address that's currently referred to, and we're able to show that, X is currently being mutably referenced by address 1, which is Y, and that is why we can't reassign the value of X, even though normally we can, because it's meant to be mutable. So now I'm going to get to the language presentation. So Oxidize is a step debugger, but it runs on a language that's also called Oxidize. And this language features stuff like immutable, mutable assignments, references, tuples, conditional expressions, ownership and aliasing, lexical scoping and lifetimes. I'll note that it doesn't feature some stuff in Rust that are quite important, for example, copyable types. The reason why copyable types aren't included, even though they're very important to understand how the borrow checker works, is that Oxidize is meant for beginners, and I remember when I was first learning Rust, I got quite confused because I would like write up snippets that only use primitives like integers, but integers are copyable, so that didn't teach me how move semantics actually worked. So I just disallow copyable types because they can just like learn, oh, this is copyable. Ownership rules don't really apply. That's simple enough. There's no type coercions because these would allow implicit dereferencing, reborrowing, reference downgrade coercions. These are quite important, but we're trying to keep this a bit like simplistic. We also don't allow traits. Traits are very important because they allow copyable, clonable, and other features, but we just like not looking at them. I'll also admit that we don't have functions yet, but that's like a to-do. Yeah. Okay, so now let's get to the grammar. So it's basically Rust with some OCaml conditional expressions. We also have unit as a keyword as an empty parentheses. And we have tuples using square brackets. So you have the standard integer type, the unit type, product types, which are types of tuples. And we have reference types, which store both the mutability and the reference type. And we also have borrow states. So we're going to first observe that a value at location L can be either moved to another location, be borrowed by reference at another location, or be dropped. which we can think about as being moved to an inaccessible location. So here are all the borrow states that I cooked up to like handle all of these three possible cases. So the reference, moved, and dropped are pretty self-explanatory. I'll note for the union, this is because of conditional expressions, because we have to unify what happens in both branches. So what the union does is states that, oh, all the states in this union are possible. So we're gonna have to handle all of them. So this is how like my rules kind of look like. So I'll note with this S, it's basically a borrow state, but it's kind of different. How they're different is explained in the paper. Anyway, so we have like our three contexts: gamma, which maps variable names to the mutability and type; mu, which maps variable names to the addresses they point to; eta, which maps memory addresses to their borrow states. And for example, if eta 0 equals ref b true 1, then the value of address 0 is mutably referenced by address 1. So as we saw on step 2 of demonstration 1, 0 is mutably referenced by address 1, so this would correspond with eta 0 equaling ref b true 1. So here are like some standard type rules. I'll also note that I created some helper functions like maydrop and drop. What maydrop does is checks that, oh, we can actually drop the value at a certain location, given our context. What drop does is actually changes our borrow checking context. All right, so we're going to go through another demonstration that has more of the features of Oxidize now that we understand what all the context stuff that appeared on the screen actually mean. So we have our type context that stores the types, the memory map that stores the muse, and there's nothing relevant in the borrow checking layout. They're all nuns, nothing fancy going on, so we don't represent anything. So now that we're going to conditional expression, we're going to allow the user to select which branch they're going to go into. Let's assume that they said true. Well, then we're going to go to the true branch. There's not much going on, so it's just one step. Now let's go to the false branch, which is a bit more interesting in my opinion. So we see here that, let's see, so like, oh, wait, shoot, I'm so sorry. I forgot, okay. So one of the things with Oxidize is that tuples, though they're 0 indexed like they are in Rust, the memory representation is a bit different, as you see here. Instead of being like C-style arrays, where the value of the pointer to an array is the same thing as the first elements, we offset it by 1. This was done purposefully so that users can know, oh, the tuple and the elements of the tuple, they're distinct notions. So borrowing one, like moving one or the other, they're quite different, as we'll see a bit later on in this example. So I went a bit too far. Okay, so we see here that 0 is partially immutably referenced. So the tuple A is partially immutably referenced, and that's because A.1 is immutably referenced by C. And whenever we're moving an entire tuple, what we do is we move all the elements corresponding to their new location. So 4 will be moved to, 0 will be moved to 4, 1, 5, 2, 6, 3, 7. And once we exit out of all the branches, we're gonna have to unify them somehow because the true branch doesn't have anything special going on. We just use the false branch. But let's suppose that true branch actually had something interesting. What we're gonna do is we're gonna use our borrow state unions to be like, oh, all of these are possible, so the next statement's gotta handle all of them. And we're going to, let's see. So like note, because this is static semantics, let's suppose that like it was like let b equals if false, then parentheses A.1. It would still say that 2 is moved to 5 because both are possible. And because we're trying to use A.1, even though it was moved to B, we get a borrow checking error as we desire because we're not allowed to use a value that's moved somewhere else. There's only one owner allowed. Now, here's our future work section. So I would like a better user interface, possibly using like a GUI, maybe something like Rust Analyzer where we have it in an IDE, and we allow the user to like use the cursor to select, oh, which location in the file they want to step at. We would like to simplify the formalism a little bit. The fact that we have like that weird S, that's not quite a borrow state, but it kind of is. I would like to simplify that in a nicer way. And figure out some design choices. So the first one is tuple indexing. I've received comments that it is a bit weird how it's 0 indexed, but on the memory location-wise, it's 1 indexed. I think it's okay, question mark, because I'm trying to like make sure that the user knows that these are distinct notions, but at the same time, it is confusing, and it's supposed to be a pedagogical tool, so confusion is kind of bad. Also, with stepping through branch unification, right now how unification works is, okay, we have the results from the true branch that we step through, the false branch that we step through, and the unification is just, okay, we have these, we're gonna, I don't like go through the unification and allow them to step through the unification process. I think stepping through would be great, but I'm unsure how to make that readable in a nice way. And there's also what to do with non-lexical lifetimes once functions are added. Currently, we only have lexical lifetimes, and non-lexical lifetimes, they offer some weird points, some awkward points on how to like step through stuff related to NLLs. For example, if a variable is no longer used, NLLs allow us to just like pretend that they don't exist anymore. But how we're going to show the user, oh, because it ain't gonna be used anymore, we can just like get rid of it. I'm not sure how to do that quite well. Maybe we could do like some control flow graph visualization, but again, that means we're gonna have to find a better interface, and a lot of these stuff are kind of interconnected and stuff. But anyways, so this has been my work so far, and all the stuff I've been thinking about recently. Thank you for listening.
We already have questions.
Thanks for the talk. If I understand correctly, you are rather debugging like the type inference instead of executing a program like GDB does.
Yes.
So in that case, I'm wondering because when you type check a program, you may have, for example, a very complicated expression on the right-hand side of a lead binding, for example, and maybe there is some type error that is related to some very, very deeply nested sub-expression. So in that case, can you also like, what is the best way to step into that? So so from the user's point of view, how should I know that there is a type error? How should I use this debugger to step into it in a convenient way?
Oh, okay. So we do have like type errors as well, but I haven't really thought about like deeply nested types. Let's see.
Yeah, I mean some expression that is deeply nested. Maybe there are some error, maybe not directly to time, but maybe some memory safety issues, whatever things that you can detect.
Okay. So like in terms of deeply nested expressions, I think that's okay because if we look at how the syntax kind of works, it's basically Rust, but like mixed with OCaml. One of the major things from OCaml is that everything's just an expression. So when we're stepping through an like deeply nested expression, it just works as though it's just like a chain of like different expressions or statements. So I think stepping through that would be okay.
Yeah, but my concern is that because in practice, if you really want to, debug a really complicated expression, it's usually hard to detect which part of it is wrong. So yeah, but I think what you are proposing is more like a single stepping approach, right? You can just click, and then you see how the type checker works. But maybe the problem is that maybe after 90 steps, I realize, oh, there is something wrong. But this is usually not, yeah, this is a hard problem, but if you can address this to some extent, I think it will become more more practical.
Okay.
Thanks.
Hey, I'm Will Creighton from Brown. I also implemented a static debugger for Rust, so come chat with me. And I wanted to ask concretely, is this interface, the ASCII representation of the type contexts with the currently executed instruction, is that as you envision it, the sort of final product? Or what is your like dream interface for presenting this information to the user? Are there ways you think that you are hoping to simplify its presentation? Or do you think this is like as the end programmer should consume it?
Well, I'm partial to like text user interfaces. At the end, I'm desiring something maybe like how Lean works. Because like when you're like proving something in Lean, there's like a separate like window that pops up and like goes through the context in a much prettier fashion. I want something like that. Yeah, I don't know, but like what the ideal interface would be is up in the air, to be honest.
Okay, thanks.
Hello, so I'm Jonas Schwela from ETH Zurich. And my question is, so you said you don't support functions, and I guess maybe you don't support loops as well? Or?
Oh, yeah, no. Sorry. Yeah.
So my question is, how hard do you think that would be to implement? Because this is like where I imagine where a lot of the difficulty comes from and where the necessity for lifetimes in Rust comes from, because you need some generalization at this point. So do you think it would be hard to add it to your language, or what is the idea there?
Well, I would assume that loops would be quite hard to add. Hence, they weren't like added just yet. Are there like any like special cases I'd have to check for? I do think so. Like for example, like let's see. Wait. Yeah, like I mean, whether we're supposed to go through like multiple passes in a loop or whether we're supposed to do a single pass, I'm still unsure about the details. I'm favoring like just like a single pass, doing like, oh, these are all the possible stuff that might happen using the borrow state union approach, but it's also like less readable. So I don't know. Yeah.
Hi, so you mentioned that Oxidize is kind of like a language and debugger designed for learning. Do you hope that, is the intention for it to be something where it kind of helps you learn maybe like Rust style ownership concepts, and eventually for like the user to maybe take off the training wheels and try other languages? Or do you see this as being used for like other, like continual use and for like professionals?
Oh, I don't think for professionals. I mean, I wouldn't use it myself besides like maybe to learn something about ownership principles. But yeah, so just for pedagogy purposes.
Okay,
Yeah.
cool.
Hi, I had a question that was sort of related to the last, so maybe actually your answer to the last kind of rules this out. But I was thinking it would be nice if you could do this like in response to error messages, where you sort of flip the order that you do things, and like we ran into an error, now you can like step back. Have you thought about like doing things like that? Or even the other thing I was thinking of as far as errors is like identifying problematic branches. So you say like we could do this if we didn't need to also unify with this branch or something. How's that, like, are you interested in doing that approach?
So for the first part, it would be quite cool to add like a debugger of this sort into like the Rust compiler itself, but like I'm unsure how that process would look like. And for the second part, I have like thought about like when we're doing our branch stepping process, because like currently you have to select which branch you want to go down, and it would be much nicer to just like tell them, oh, is the false branch that is problematic or is the true branch that is problematic? But I'm unsure whether we'd be able to always detect which branch is incorrect. So yeah, I don't know, I haven't thought about that like too far.
So I just have a slight suggestion. Where you were saying about the tuples and having the addresses, have you considered using address ranges? Because then you could talk about the tuple being the range 0 to 2 or 3, I can't remember how long it was, and then the individuals could be the individual parts of that range. So then you could have it as a, not having to have a separate entry.
Oh, I haven't thought about that, but thank you for the idea, yeah.
That's all the questions. So,
great.
Yeah,
Thank you.
Thank you.
Get my phone and take a picture of the room so people believe that people came. Yeah, so as the last organizer standing, as I said at the beginning of this session, I would ask people what they would like to do for the next session. Options range from just getting out to the pastries to coming back and talking about potential future work, or asking more questions of the speakers, or just basically going off to Cascades to the pub. And I'd be offended whichever way we turn out. Yeah, so I don't know what people would like to do. Have I thought of any wider way of doing this? Well, look, I'll wander back here after the thing, and if there's anybody here who wants to talk about stuff, I'll be here. And if not, yes.
I think it would be pretty nice to have like the speakers here and have an informal panel in the sense that I'm sure we are working on so similar topics that if we just throw a conversation, it will do something nice.
Well, I think so too. All right, we'll be here if you want to get on with that.